Hi everyone, welcome once more to Best Science Brain YouTube channel. Today we are still taking a look at advanced organic chemistry and we're looking at aldehydes and ketones. So this video or this tutorial is meant for students in high institutions, in tertiary institutions, and those who are offering organic chemistry, and also for those who are doing their postgraduate studies in master degree. So not only for undergraduates, but also those who are offering organic courses in postgraduate studies or master degree in chemistry, pharmaceutical chemistry, and then natural product chemistry. So today we're going to start with uh, two carbonyl compounds, aldehydes and ketones. Aldehydes and ketones, carbonyl compounds. So we're going to look at the reactions of aldehydes. But first of all, we're going to start with nomenclature of aldehydes and ketones. Under nomenclature, the common system and the IUPAC system of naming aldehydes and ketones. After the nomenclature of these two unique compounds, we'll now look at their reactions, the nucleophilic addition reactions of aldehydes and ketones, and also the addition and elimination reaction of aldehydes and ketones. So that is what we have in this package. We're not going into reduction reactions or oxidation reaction by the hour. We're not also going into condensation reaction of aldehydes and ketones. That'll be in the next package. But today our focus, as I said, will be on the nomenclature, the nucleophilic addition reaction mechanism, and then addition and elimination reaction mechanism of aldehydes and ketones. So today we're going to start with these two unique compounds. So stay connected. If you're not subscribed to the channel or you're seeing the channel for the very first time, please locate the subscription button under the video as it's playing. Tap on it only once and get subscribed to the channel. Share a video to students in high institutions, in your school or in different schools, and to those who are also offering postgraduate studies or offering chemistry-related courses that will help them also to understand chemistry better. So welcome constructive criticism and we also welcome comments in the session. Any question will also be attended to. So this is for those in high institution. We're also still going to do videos, raw videos for those at O level or grassroots very soon. So after this lecture, the next video we're going to present will be physics and chemistry lecture for those in WAEC or NECO O level school certificate examination. So we are going to start with this. So stay connected as we now start this lecture. So we should know that aldehydes and ketones are carbonyl compounds. So they are carbonyl compounds. So what do I mean by carbonyl compound? That they possess the carbonyl functional group. The carbonyl group is depicted on the board. Carbon linked to oxygen with a double bond. They have this. This is the carbonyl group. So aldehydes and ketones, they have the carbonyl group as their functional group. So this carbonyl group is a polar group. It's a polar group in that if we see the structure in this form, you see the same thing. See, they are the same structure. So if you see the structure in this form, so this pi bond can be delocalized so that this also being more electronegative will pull the electron to itself, giving you this structure. So you see that, making the oxygen partially negatively charged and the carbon atom partially positively charged. So that was what I mean, that since oxygen is more electronegative, the bond is polar. So this bond can be this electron can be taken away by oxygen to give oxygen a net negative charge and carbon a net positive charge. While sometimes we can still present the bond in this form or the group in this form. So we can still present in this form, whereby we give the oxygen partial positive and this one partial negative. So that is the way of representing this aldehyde and ketone. So one of them is okay, whether it is in this form or in this form, whereby the pi bond have been shifted to oxygen. Oxygen being draws the electron to itself, or we give carbon partial positive and partial negative. So aldehydes and ketone are characterized by that functional group we have on the board, the carbonyl group. So now, what's the difference between aldehydes and ketones? Since both of them possess the carbonyl or functional group, the difference is this. For the aldehydes, for the aldehydes. The carbonyl group, look at the carbonyl, is the carbonyl carbon is bonded to one alkyl group on one hydrogen atom. So that's the general structure of the aldehyde. The carbonyl carbon is bonded, this is the carbonyl carbon, call this carbonyl carbon. Why we call this one the carbonyl oxygen? So the carbonyl carbon, then the carbonyl oxygen. Why the CO is called the carbonyl group. How do you understand that? So the carbonyl carbon and the carbonyl oxygen. So that is it. So in aldehydes, the carbonyl carbon is bonded to one alkyl group. You know the alkyl group, we have already done that in our previous videos. The alkyl group like methyl, ethyl, propyl, obtained when you take away one hydrogen from an alkane. Like the alkane that is a CH4 methane. Take one hydrogen, you get, let's do it this way, methane, CH4, one hydrogen, you get methyl, Ce2H6 ethane, one hydrogen, you get ethyl, Ce3H8 propane, take one hydrogen, you get propyl, Ce4H10, take one hydrogen, you get butyl, Ce4H9. So any of these stand for an alkyl group. So any of them can be fixed here. So in aldehydes, the carbonyl carbon is bonded to one alkyl group, which could be any of these, and then one hydrogen atom. That is an aldehyde for you. So for example, let's look at this. CH3, this is an aldehyde. So this aldehyde, are you seeing it? So that is an aldehyde for us. So, and then it's called acetaldehyde. Acetaldehyde. So that is it. So in aldehydes, you have one carbon atom. The carbonyl carbon bonded to one alkyl group and one hydrogen. But there's only one aldehyde. Okay, look at the example aldehyde before we go to the examples and what I want to talk about. This is, if I put a T group here, and then this. So this is called propion aldehyde, 3 carbon. Propion aldehyde. So that's an aldehyde for you. So these aldehydes also have their IUPAC names, but we are using the normal name. They have IUPAC names. This one that has 2 carbon, because that kind that has 2 carbon is called ethane. Can also be called ethanol. This is the IUPAC name. This is the common name. The one that has 3 carbon is called, can also be called propanol. But that kind that has 3 carbon, propane, the common name and the IUPAC name. So we are here to go to nomenclature, but we're trying to envisage or study the structure of aldehydes for now. So you see how aldehydes look like. So we have one alkyl group linked to the carbonyl carbon, and the other atom will be hydrogen atom. We'll call such compound aldehydes. Then the only one aldehyde that does not have an alkyl group, that only have 2 hydrogen atoms. An exception to this rule, the aldehyde called methanol or formaldehyde. Look at this. There's an aldehyde of this nature. That's the exception to this rule, whereby you don't have one alkyl, rather you have 2 hydrogen bonded to the central carbon or the carbonyl group. So this aldehyde is called methanol, or the formaldehyde, the old name or common name. Then methanol, which is the IUPAC name. So what I was saying here, we'll say that for you to recognize an aldehyde, you have the carbonyl group at the center. Then close to the carbonyl group, you're going to see 2 atoms bonded. One of the groups must be an alkyl group, which I have listed some of them here. And the other will be hydrogen atom. That's how aldehyde look like. Then the only aldehyde that doesn't have an alkyl group, that has only 2 hydrogen on both ends, is called formaldehyde. So having understood the structure of aldehydes, we now go to ketones. Ketones also possess the carbonyl group, functional group, so that they are carbonyl compounds. But in ketones, we have this structure. two alkyl groups, which could be the same or different alkyl groups. Two alkyl groups bonded to the carbon of the carbonyl group. Look at ketone, and then look at aldehyde. See the difference between the two of them. See aldehyde, one alkyl and one hydrogen. Ketone, two alkyl groups, no hydrogen on the central carbon. This is called a ketone. Example, this alkyl group can be CH3, CH3. So that is ketone. Two alkyl groups on the carbon atom bearing the carbonyl oxygen. So this is called acetone. The common name, propanone. The IUPAC name. Common name acetone, propanone, the IUPAC name. Then this alkyl group acid can be the same or can be different. Another example is maybe you have C2H5 on this side, then the carbonyl carbon, and then CH3, which can also be drawn like this. It's also writing CH2. You can break it into CH3, CH2, then that. So these two compounds are the same thing. Because you compress this, adding the two carbon, you have C2. Add this, you have 5. It's very easy to understand. If you draw this the full structure of C2H5, it's going to be 2 carbon and then 5 hydrogen. So you see that. So that is CH3 and then CH2. So CH3 and then CH2. That is C2H5 when you compress it. So you have that. So this same time as ketone, you have two alkyl, but this time around two different alkyl groups. So an alkyl group here and also an alkyl. It's still a ketone. We call this ketone methyl ketone. So not to worry, we're going to nomenclature and we're going to learn how to name them very well. But now we're trying to investigate how to identify aldehydes and how to identify ketones. So that's our main issue now, how to identify aldehydes. So as I said, this one is called acetone, or you can still call it propanone. That's the IUPAC name, propanone. While one is called methyl, then ethyl ketone. So having done that, we're now going into how to name aldehydes. We'll now look at nomenclature of aldehydes. To name aldehydes, we want to start with the common system first. The common system. Before we go to the IUPAC system. To name aldehydes, first of all, you have to understand how to name monocarboxylic acids. Monocarboxylic acids or monoalkanoic acids. I have to understand how to name these kind of acids. From here, I can then know how to name aldehydes. So, monocarboxylic acids have the formula RCOOH. That's their general formula. Which this is the alkyl group, which I'm using as CnH2n plus 1 COOH. So this is the alkyl group. That's the formula for the alkyl group, and then the functional group is there. Now for these acids, N start from 0. N start from the number 0. To get the first member, what I'll do is I'll replace N with 0. I have C times 0, H2 times 0 plus 1, then COOH. So 1 carbon times 0 is 0. That's 0 is carbon is eliminated. 2 times 0 is 0 plus 1 is 1. So that'll give me 1 hydrogen remaining. 2 times 0 is 0 plus 1 is 1. That's 1 hydrogen and then COOH. To get its common member, I'll use N as 1 now. First member N is 0. So you have a C1 H2 times 1 plus 1 COOH. When you do that, you're going to get 1 carbon. 2 times 1 is 2 plus 1, 3. That is H3 COOH. Okay? To get other members, I can use 3. use 2 now for the second member, or I'll be adding CH2 since a homologous series, each member different from the by CH2. That is, keep the functional group constant. 1 carbon comes down, then 2 plus 1 gives you 3. Then keep the functional group constant. Then add 1 carbon plus it gives you 2. Then 3 plus it gives you 5. Are you seeing what I'm doing? Then keep the carbon functional group constant. Then add to this group. 1 plus 2 gives you 3. 2 plus 5 gives you 7. So keep the carbon atom constant. You have C4. Keep the functional group constant. You have 1 plus 3, 4. 2 plus 8 gives you 9, H9. You can generate the members. So either you substitute this one by this one, now use 2 for substitution. You can see that. You now have C2. 2 times 2 is 4 plus 1, 5. The functional group. They substitute here with 3. Have that. C3. 2 times 3 is 6 plus 1, 7. Same formula. So either you do it by substitution or you keep on building it by adding CH2 to the non-functional part of the compound. You generate the members. So these are organic acids or the monoalkylic acids. So unless you understand how to get the names or formula of the monoorganic alkylic, you cannot be able to name aldehydes or get formula of aldehydes. So having done that, let's now look at these members now again. I'm going to write them on the left-hand side of the board. We have HCOOH, CH3COOH, C2H5COOH, C3H7COOH, C4H9COOH. The next member will now be C5H11COOH, and then the other member will be C6H13 by adding CH2 continuously, so and so on. Now let's see the names of these acids. How would the name go like? How does the name go like? This first acid is called methanoic acid. Methanoic acid. This one is called acetic acid. This one is called propionic acid. You see? One is called butyric acid. This one is called, this is the fifth one, valeric acid. Then this one is called that is 6 carbon, caproic acid. While this one is called enantic acid. I think that should be spelling. So that is it. So these are the common names of this acid. So we want to get the common names of the simple aldehydes. We look at the simple aldehydes. So the simple aldehydes. So get the simple aldehyde. What I'm going to do is this. You watch what I'm going to do. I'll replace the functional group of the, in each case, the functional group, the carboxyl group, the COH, replace with the carbonyl group. And I have HCHO. The carbonyl group is, remember, is this. For the aldehyde group, we're going to have a H here. So you place the COOH with CHO in each case. This one now becomes CH3, CHO. Replace this with CHO. The one now becomes C2H5, CHO, C3H7, CHO, C4H9, CHO, C5H11, CHO, then C6H13, CHO. So what I've done is replacing the carboxyl group in each acid with the functional group of the aldehyde, which is CHO. You see that? Then how would the name sound? In each case, we'll now remove this one. The error here, I use the IUPAC name. We'll talk about the common name. The common name of that acid is formic acid, please. Here I use that this formic correction. We're talking about common system, not IUPAC system. So formic acid. Now, to name the aldehydes, what do we do? In each case, remove the IC in the name of that acid. Remove the IC and put aldehyde. So this is now called formaldehyde. The one is called acetaldehyde. The one is called propion aldehyde. The one is called butadiene. This one is called valenaldehyde. One is called capiroaldehyde. So this one is called enantialdehyde. So and so on. So you see the names of or how to generate the common names of aldehyde. Very simple. So you start by first of all knowing how to derive the formula of the monoorganic acid, as I taught you, monocarboxylic acid, and then how to name them. Then from the formula, you can get the formula of the aldehyde by replacing the carboxyl group COOH by CHO in each case. See that? And then when you have done that, then after the naming, replace the IC in each name of that by aldehyde. We now get the simple aldehydes. So having done that, we now look at how to name the substrate aldehydes. We now learn how to name the substrate aldehydes in the common system. So, substrate aldehydes. I'll give an example. For how to name that substrate aldehydes, how to know how to name the number the carbon or give number to the carbon atoms on the longer chain. For instance, let's say we have this. Okay. And then this is the terminal aldehyde group carbon. So we'll have this kind of chain. How do we number the chain? The carbon atom closest to the aldehyde group, closest to the aldehyde group is named alpha. The next one is called beta. One is called gamma, and one is called delta, and so on. So we use Greek letters. The carbon atom closest to the aldehyde functional group is called the alpha, after the carbon of the aldehyde or carbonyl carbon. Alpha, beta, gamma, delta, and so on. So assuming that we have this compound, we have a CH3 here, hydrogen, and then you have to name this aldehyde by the common system. To name this aldehyde by the common system, what do we do? So we have to, this is the alpha carbon. So that the alpha carbon, carrying the substituent, which is the methyl group, is the functional group. So we now call this alpha methyl. And then we ask ourselves, how many carbon atoms are we seeing here? We're having 1, 2, 3, 4, 5. 5 carbon represent valenaldehyde. So we now call it valenaldehyde. So aldehyde that has 5 carbon is valenaldehyde. So we now say alpha methyl valenaldehyde. Joining the names together without spacing, valenaldehyde. So that is the full name of this compound by common system. Okay, so assuming that we have another example here, whereby maybe let's say we have two substituents. Perhaps we have here again another methyl group. So how will we name this aldehyde? To name this aldehyde, this is the alpha carbon, this is the beta carbon. You start numbering from closest end to the functional group, please, not from this end. This is where you have the functional group number 1. Then so alpha, beta, no other substituent here. When I call this alpha, beta, there are 2 of them of the same kind. That's a hyphen, dimethyl valenaldehyde. So you can see that alpha, beta, dimethyl valenaldehyde. So very simple to name. So assuming that you have this, there's another example. They have take another example here. So have 1, 2, 3, 4. So they get it right. 1, 2, 3, 4. So this one carries the methyl group. And then you have the aldehyde group. and then 1, 2, then this one, we have a branch chain here. The branch chain giving us CH2 and CH3. So how do we name this compound? Now, in this case, this was an aldehyde. To name this aldehyde, what do we do? We'll start from the functional group end. This is number 1. Then the carbon close is called alpha. But first of all, let's identify the longest chain. 1, 2, 3, 4. The straight chain gives us 4. 1, 2, 3. The branch chain gives us 3. 3 less than 4. 1, 2, 3, 4, 5. Look at the longest chain. 1, 2, 3, 4, 5. That is 5 carbon chain. So you have to find the longest chain, but not be a straight chain. So according to the convention we use in organic chemistry, the longest chain, it mustn't be a straight chain. Longest chain, straight chain giving us 4, but this is, we have a carbon chain giving us 5. So this is the longest chain. You can see that going like this. So this is the alpha carbon. You number the carbon atoms on the longest chain only. Alpha, then beta, then gamma, then delta. So you can see that. Alpha, beta. So you don't number the carbon atoms that are not on the longest chain. You have to know that. So these carbon atoms are not part of the longest chain. So you have to number the carbon atoms. Remember that you don't give any letter to the carbon of the carbonyl group. The nearest to it is the alpha, then beta. I wouldn't go like this because it's not the longest chain. I will not go like because it's not the longest chain. I'll move to the longest chain, beta. The longest chain must not be a straight chain. In this case, the branch chain, beta, gamma, delta. And then we have 5. 1, 2, 3, 4, 5. That depicts valet aldehyde. That is 5 carbon aldehyde. Then these are the substituents. This is not a substituent because it's not numbered. This is also a substituent methyl group. So the methyl is on alpha and beta carbon. Now call it alpha beta dimethyl valet. They are the same kind. I think that is example I was to before now, and they are the same structure, but this one is twisted in the previous example, and this one they are the same thing, but this is twisted, so to still give you the same nomenclature. So alpha beta dimethyl valet aldehyde. So having done that, now what if the aldehyde bears 4 carbon atoms? They say 1, 2, 3, 4. So an aldehyde with 4 carbon atoms is called butadiene. So let's say we have this, you have to name this. So how will you name the compound? So you see that. So this aldehyde has 4 carbon atoms, and the 4 carbon atoms are all in a straight line or straight chain. So there's no branch carbon chain. This is chlorine, this is not carbon. So this is 1, 2, 3, 4. That is butadiene. So let's now number the carbon atom. This is alpha, this is beta. So this is gamma. So the substance is on this one. So this is now called beta chloro butadiene. So you see how to name aldehyde by the common system. We'll now go to the IUPAC system of naming aldehydes. The IUPAC system is very simple. The same way generate organic acid. So look at the acids again. We have this one. In the IUPAC system, this is not called formic acid again. This is now called methanoic acid. The next one, CH3, we generated before. You can go back to the video and see it. This is called ethanoic acid. Then the next one, C2H5. This is called propanoic acid. The next one, C3H7. This is called butanoic acid, and so on. So how do we name? I can see take the other one, C4H9 pentanoic acid. So how did I generate these names? It's very easy to generate. To generate these names, all you have to do is you count the carbon atom. The first carbon is 1. The alkane that has 1 carbon is called methane. Methane. So go to 1 carbon, now methanol, remove the E and E At the end of methane, I put OIC, methanoic acid. The alkane that has two carbon in all is called ethane, now ethanoic acid. The alkane that has three carbon can count 2 plus 1, include the one in the functional group, 2 plus 1, 3, propane, propanoic acid. 3 plus 1, 4, butane, butanoic acid. 4 plus 1, 5, pentane, pentanoic acid. Then the aldehydes by the IUPAC convention. How do we name them now? So by IUPAC convention, or let's get the formula first. Get the formula, you know, after all, we are studying how to get the formula. Remove the functional group and put CHO as we did in the previous common system. CHO, CHO, CHO. So taking away the C functional group, that is COOH, and replace them with CHO in each case. You have the aldehyde compounds. So the name, to name it, we now remove the OIC, and call this one methanol. In IUPAC system, aldehydes are called alkanals. Alkanals. You see they end with AL. So remove the OIC and put AL, methanol, ethanol, propanol, butanol, and then pentanol. So we now get the IUPAC nomenclature. So let's look at some examples of substituted aldehydes in the IUPAC nomenclature. So the aldehydes in the IUPAC system. So let's see how it goes. So look at the substituted aldehydes. So what done by substituted aldehyde? When the hydrogen atom in the carbon chain replaced by another group, we now have the substituted aldehyde. So you can have this example. Okay. So you can see this. So this is an aldehyde. So if you want to open the chain, you can open the chain yourself. It's very easy to do. And then after opening, you can name the structure. Or you can still name it the way it is, so no wahala. There's no problem here. So if you want to name this, so you start from numbering the carbon atom closest to the functional group, that's the key group. So you have number 1 and number 2. 1 and 2. Then to know it's only a straight chain, there's no branching of carbon. So these are not carbon atoms. So it's a straight chain. So 3, 4, 5. 3, 4, 5. And that has 5 carbon atoms. It's called we call it propanol. So the solid is number 2. This is now called 2-chloro. It's not propanol, sorry, pentanol. 2-chloropentanol. Propanol is when you have 3 carbon. 2-chloropentanol. The names all joined together. Number separated from word with hyphen. 2-chloropentanol. So you see how to name aldehydes. So what if I have this CH3 here and chlorine here? So how would I name this aldehyde? By IUPAC, this is a substituted aldehyde. By IUPAC convention, well, we'll still have to number using numerical values, not alpha, beta, not Greek letters, using 1, 2, 3 from the functional group. Number 1, number 2, number 3, number 4, number 5. We have 2 substituents here, methyl group and chloro group. So which of them is named first? We now separate them by alphabetical order. Chloro start with C, methyl start with M. So chloro comes first. We now have C come before M. We now call it 4-chloro hyphen 2-methyl and then pentanol. Because look at the naming sequence, the chlorine C letter comes first English letter alphabet before comes before M alphabet. So that's the name of this aldehyde. So it's very easy to name aldehydes by IUPAC system or by conventional common method. Let's take another example of this structure that looks complicated. You can see that the phenyl ring derived from benzene. So you have that. You can see that. So now I have CH2. You can see that. And then CH3 here. And then of course CH2 here. So you look at this structure. Let's attempt to name this compound. So, okay, here is CH3. Oh, that ends here. So let's attempt to name this compound. To name this compound, so what do? We'll start by numbering the carbon of the functional aldehyde, identify it. After you've done that, the longest carbon chain, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Longest chain remains 4, the straight chain. So we now have 1, 2, 3, 4. So we have two substituents here. We have this is not numbered because not part of the longest chain. Methyl group. Methyl start with M. This group is called phenyl. Phenyl. Instead of writing this, someone can say write C6H5 in place of this. That's the same thing. The same phenyl, the same structure. So obtain when benzene loses one hydrogen. So this is attached here. Can be also be attached in place of this structure. This can be written here. So having done that, so look at the alphabetical order. M comes before P in English alphabet. So to name it, M comes first. Now I say 3-methyl. 3-methyl hyphen. Then this is also this number on number 3 is also number 3 carbon. 3-phenyl. You can see that. 3-methyl and 3-phenyl. Then the aldehyde has 4 carbon atoms on this longest chain. And the aldehyde that has 4 carbon atoms is called butanol. Now ending with butanol, joining all the ways together. Butanol. So that is the name of this aldehyde. 3-methyl, 3-phenyl, butanol. Okay. Then also, before we go to, we're now going to ketones. Before we go to ketones, we have to refer back to the common system again. That's something we forgot. We have to do it. The common system, even though we did it first, but there's some nomenclature we forgot we have to put into place before we go to ketones. Sometimes another functional group can coexist with the aldehyde in the same compound. For example, look at this structure. Okay, we now have the aldehyde group here. So you can see that structure. So you see that another functional group is coexisting with the aldehyde. So in this case now, the aldehyde group will now function as a substituent group. Why this one will be taken as the key group? Because if you number it now, you number from this end. This is number 1, number 2, number 3 carbon here. So that means the functional group is taking a lower number or lower preference compared to the aldehyde. So the functional group, the double bond, you have a lower number, and the aldehyde group have a bigger value. In this situation, where the aldehyde, the functional group is precedes or has a lower number than the aldehyde group, but the common system we won't call it again. Will not call it an aldehyde. So the compound will not end with aldehyde. This group is now called the formyl group. Formyl or formyl group. Formyl group. So now the compound will now go by the name 3-formyl, that portion of the aldehyde group. Aldehyde now is a substituent. There is a cyclo chain, cyclohexene or cyclohexene, because this is double bond, take number 1. So 4-formyl cyclohexene. So you can see that. So because in this situation now, the aldehyde is not the principal group. and not taking the lower number. So we're going to give this one the parent name. You see the difference. Look at another example of this common nomenclature, whereby you have this benzene ring. This compound is normally called sulfonic acid in chemistry. Sulfonic acid or benzene sulfonic acid in chemistry. So let's assume that we have an aldehyde group here. So we have seen that in this compound now, the aldehyde group is not the first group here, or the major group is acid group, the sulfonic acid group. So we'll call this carbon number 1, number 2, number 3, number 4. So in this situation, now the same rule apply. We'll now call this 4-my. That is based on this. Then benzene sulfonic acid. So this is the common name of naming such, common system of naming such compounds. So having clarified the common system very well, and then seeing how to name aldehydes both in common and the IUPAC convention, we'll now go to ketones. Ketones, how to name ketones. So how do we name ketones? Ketones, as we said, normally have two alkyl group linked to the carbon of the carbonyl group. So to name ketones, we'll have to first of all, by a common system, let's look at the common system of naming simple ketones. As I say, these alkyl groups can be the same or different. So let's say have CH3, CH3. By a common system, this is called acetone. It's called acetone. Acetone, because remember that okay, acetone, that is from acetic acid. This is acetic acid, CH3 COOH. This is acetic acid from common name. If I remove the hydroxy OH and bring in this, so that means derived from acetic acid and bring in another alkyl group, we call it acetone. So this is how you name aldehydes, by the common system. So having done that, moving. So now the question is this: what if the alkyl groups are different? For instance, I have CH3, CH2, C, and then here CH3. So if they are different from each other, so look at this side. This side can be compressed as C2H5, if you know that. Then carbonyl group, then CH3. Two different alkyl groups. So what if they are different? How do I name this kind of a ketone? To name this ketone, what would I do? Since they're different groups, I will not just call it acetone because they're different groups. What would I do? What I'm going to do is this. Out of these two, I ask which of them has a bigger magnitude, which of them has a bigger molar mass. This one contains 2 carbon. This one contains 1. So this one will have a smaller molar mass. This one will have a bigger molar mass. So name the one that has a smaller molar mass first. Whether it's on the right hand side, left hand side, or on the right hand side, doesn't matter. So out of these groups, name the one that has a smaller molar mass. Is this one that has 1 carbon. This is called methyl. After that, give a space. Then name this one, which is called ethyl. And then ketone. End it with ketone. See the way it goes. Methyl, ethyl, ketone. So let's take another example of how to name ketones, simple ketones. So, for example, let's say we have this CH3, CH2, bracket 2, C, and then CH2CH3. You have to name this ketone. So this is a ketone. But I hope you know that this is second as writing CH3. This is bracket, means that methylene group repeated twice, CH2CH2. Then link to this. Then this sentence as the compound written above. That is same. That is opened up. Or you can count the carbon. 1, 2, 3. That is C3. Hydrogen 5 and then 7. 3 plus 2 plus 2, that is 7. So that is this. I can compress this as C2H5. So this structure, this and that are the same thing. To name this ketone, I look at these two groups. Which of them is smaller magnitude? One has 3 carbon, this one has 2 carbon. This is smaller. And then this one, this is ethyl from ethane. Ethyl, then this one from propane, 3, propyl, then ketone. So you see how you name ketones by the common system. So we'll take another example of naming ketones. Another example is this compound, CH2, double bond, then the functional group, and then CH3. So this is a ketone. You can see an unsaturated group on the left-hand side, and then the alkyl group on the right-hand side. So it's a ketone. So if you look at these two groups, this side, this one is a smaller one carbon. This is 2 carbon. This one goes first, methyl, and then 2 carbon. This group is called vinyl or vinyl. That is 2 carbon. Then ketone. You see. So that way, how to name ketones. Then look at another example. Let's say we have a phenyl ring, C6H5, ketone, then linked to CH2, then how many CH2? 3 CH2 and 1 CH3. This structure can also be drawn like this. If I don't want to write it, I can just draw this structure. This is the same thing as this. A benzene ring that has lost 1 hydrogen. Then CH2, 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 CH3. So to name this ketone, this one's of higher magnitude, 6 carbon, only 4 carbon. So this one will be named first. This is called butyl. Then followed by this one called phenyl. Then ketone. Butyl, phenyl, ketone. So let's look at the IUPAC nomenclature of ketones, of some ketones here. Mainly let's look at the simple ketones before we now go to the substituted ketones. For example, let's say we have this. Remember that this is certain as CH3. See, if you want to open the structure, you see the same compound. You have to name it by IUPAC nomenclature. You don't call it acetone. In this one, you count the whole carbon. 1, 2, 3 carbon. And ask yourself, which alkane has 3 carbon atoms? The alkane that has 3 carbon atoms is called propane. We now call it propanone. Remove the E and put O-N-E. That is why in the IUPAC system, ketones are called alkanones. So propanone, you can see the way it goes. So another example is perhaps we have a CH3, CH2, CO, CH3. You can also be written as the CH3, CH2, carbonyl group, CH3. So you can see that. By IUPAC nomenclature, you count the whole carbon. 1, 2, 3, 4. 4 carbon. Alkane is called butane. This is now called butanone. See the way it goes. Replacing the E after butane with O-N-E. Now let's look at this structure again. Under structure and example, we have CH3, CH2, and then this one CO, CH2, CH3. To name this compound, what would I call it? This is our number. This is number 1, number 2, number 3, number 4, number 5. So the carbonyl group is on number 3. This is called tripentanone. Because of 5 carbon, the 5 carbon alkane is called pentanone, but the carbonyl group is number 3 carbon, position 3. That is tripentanone. Now, some may ask, why didn't I call this one 2-butanone? Because if the carbonyl group is here, it will be number 2, 1, 2. If I put it here, Let's say I put it here, still be 1, 2. There will be no difference in whether from this side or from this side. So that one will ignore the number 2. But this one, if the carbonyl group is here number 3, if I put it here, let's draw it another way and see how it goes. You see this. These two compounds are isomers. You look at the carbonyl, let me draw it up and make it clearer. This one, CH3, see, so you can see that this compound is different from this, but they are similar anyway. So if you are number 8, this is number 1, number 2, number 3, number 4. So the carbonyl group has shifted, no longer on number 3. But it still has 5 carbon, pentanone. So I'll call it this one 2-pentanone, the isomers. 2-pentanone, 3-pentanone. See the reason for the numbering. So the situation whereby if you count the carbon atom to the right hand side or the right hand side, the carbonyl carbon can shift position and take another number, then you have to bring in the number. But if you count it from both sides and put change the carbonyl compound to different position and there is no change as in butanone, you ignore using 2-butanone. So, having done that, we can have other examples. Let's look at small complex examples. Like this case, CH3 linked to carbonyl compound, carbonyl group, CH2, then C, carbonyl again. So have 2 carbonyl groups here. So, and they have equality, they are equal because they're the same functional group. So when I start from this end, I'll have 1, 2, this end also 1, 2. So any end can go. So I have this end 1, 2, 3, 4, 5, or 1, 2, 3, 4. So any end is going to be 2, 4, 2, 4. Now this ketone has 2 functional groups, so call it a dione. So because of 2 functional groups, it's called a dione. So there are 5 of them. 5 would have been pentanone, but it's now called pentadione. Pentadione. We have to take into cognizance the position of the functional group. So this is number 2, number 4. This is now 2, 4, pentadione. 2, 4, pentadione, or you can still call it pentan 2, 4 dione. That is acceptable. Pentan 2, 4 dione. So you can see that penten. Okay, this should be penten dione. Then pentan 2, 4 dione. So that is the same compound. So this is also a complex structure. Then we have this example again, whereby you have a phenyl ring, CH3, C, then CH3, then a phenyl ring under, then we move on. We now write CH2, CO, and then we have CH2, CH2, CH3, CH2, CH2, CH3. You have to name this ketone. So how we name the ketone? That equation, how we name the ketone? To name it, identify the functional group. The functional group is the carbonyl group. So check both ends. Which end give you a smaller number? Okay, a smaller number to the longest chain, of course, remains 1, 2, 3, 4, 5, 6, 7. The longest chain. Branch chain is 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. Still remains 7. So we can take the straight chain being also the same 7 at the longest chain. You now number it from the end. I give this number, this carbon, the smaller number. This is 1, 2, 3, 4. 1, 2, 3, 4. So that is it. Then how do we start numbering? But we have substituents somewhere. Have our substituents there. The substituents are on phenyl and what? Methyl group. So we have to respect this group first. Gives us this one preference. This is 1, 2, 3, 4, 5, 6, and then 7. So you see that. So we have to give this the functional group a smaller numbering from whatever location we want to start. a small membrane. If not, that'd be wrong. So, having done that, what will be the name of the compound? The compound is now called, the substances are on number 6 each. So methyl and phenyl. So methyl takes a smaller number. We'll now say 6 methyl, 6 phenyl. So it's 7. And 7 is a heptane, but it's not is a ketone. Now call it heptanone. Heptanone. 6 phenyl methyl, 6 phenyl heptanone. So you can see that example on the board. We'll take another example whereby the cyclic structure of this form, cycloketone. So you see that this is a ketone, but the cycloketone. To name this compound, this is number 1, number 2, number 3, number 4, 5, and then 6. So 1, 2, so that is to give you 1, 2, 3, 4. It's okay. Our interest is giving the functional group the smallest value from whatever end you want to start naming, whether it's moving anti-clockwise or clockwise. So you have 1, 4, also 1, 4, move like this. So this is a 6-membered ring. So it has 6 sides. So that means the cyclohexanone. So because there are 2, we have to say the position we have to say 1 for cyclohexandione. Because the di comes because we have 2 functional groups. And then the position 1 and 4 show the position of the functional group. 1 for cyclohexadione. We have another example like this one. Have CH2, CH, in the double bond here, and then CO, and then CH3. So to name this compound, so where do we start from? We have to make sure that we give the ketone, the functional group, a smaller number. So now have, you see, the compound is not saturated. It's already got a double bond. So this is number 1, number 2, number 3, number 4. So how do I name this compound? This compound is called trebutene. 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 So the compound trebutene. Why is it called trebutene? That 2 show the position of the carbonyl group. The double bond lies between carbon 3 and 4. We'll take a smaller value. Trebutene. So that's how we'll name this compound. We'll take one or two examples, and then we'll move over to what we have today. Move over to the reactions of carbonyl compounds. So let's look at this example. How will I name this compound? This is an aldehyde. We have to take a general nomenclature. An aldehyde because of this group. So this can be this, or can be written as CH2, system 10, CH3. So to name this compound, what would I call it? This is a cyclic structure, 6-member ring. So with this is number 1. This is where I had the function with number 1 carbon here, and then number 2. So this is a cyclohexanone. So we now call it 2-ethyl because of this group. Prefix, substituent group, 2-ethyl cyclohexanal. Sorry, hexanal is an aldehyde, CHO, not a ketone. Cyclohexanone. Hexanal, sorry. So one more example, move off to another thing. One more example, we have this. Have this structure. Yeah. Have CH3 here. Have CH linked to branching. CH3. So that is it. You look at this structure. This compound belongs to the ketone class or decanone class. So how would I name this compound? Now to name this compound, what I'll do is identify the functional group. So number 1 carbon here. So I'll move like this and say 1, 2, 3. 1, 2, 3, 4. This side 1, 2, 3. This one give me a shorter, smaller number. So I'll move in this way. 1, 2, 3, 4. Okay. So the substance are here, number 3 and number 4. So what the name of that CH3 group? The CH3 group is called methyl group. Methyl. Why this one looks like propyl, 3 carbon, but the carbon is branched. The group is branched. Carbon linked to another. So this branching, we don't call it propyl, we call it isopropyl. Because of the branching of carbon to 2 other carbon atoms. Why this is called methyl. So look at this. So you see that in nomenclature, Abeka order, this one comes first in I, come before M. So we'll now call it 3-isopropyl hyphen 4-methyl cyclo. Let's complete this side. Cyclohexanone. Cyclohexanone. 3-isopropyl 4-methyl cyclohexanone. So having done that, we'll now move over to the reactions. So we'll now start with the reactions of carbonic compounds. We're going to start with the nucleophilic addition reactions, and we'll explain the meaning of the nucleophile in organic chemistry. A nucleophile is a reaction intermediate, which is electron rich and loves to attack a positive or electron efficient center. So, carbonic compounds, in our previous video, we studied the nucleophilic addition reaction, which occurs mainly in alkenes and alkynes. So, but today we're looking at nucleophilic addition reaction. Then, before we go on to that, we have to understand the carbonyl functional group very well. The bonding here, carbon, remember carbon is tetravalent, have valency of 4 around it, 4 electrons around it. Then with these 4 electrons, it makes a bond with another atom this side, giving a single bond. And make another atom bring another bond here, remaining 2 electrons. Those 2 electrons on carbon will now use to form a bond with oxygen atom. Oxygen has the number of 8, which is 2 6. It has 6 valence electrons. So let's say this is number 1, number 2, number 3, number 4, number 5, and number 6. So oxygen will now bring 2 electrons to form a bond with carbon. So when the 2 electrons come up here, we now form a double bond, 2 pairs shared, a double bond located here. So that means the central oxygen here has 2 lone pairs. So that should be 2 lone pairs located on the oxygen atom of the carbonyl compound, or the carbonyl functional group, sorry. And as we say, this oxygen is slightly electronegative, or electronegative, while the carbon is slightly electropositive. So now, going over to the nucleophilic addition reactions of carbonyl compounds. The first we're going to treat is the one that normally involve acid catalyzed. We look at the acid catalyzed nucleophilic addition reactions. So, which normally involve, one is hydration or addition of water. And number 2 is addition of alcohol. So these 2 fall under acid catalyzed nucleophilic reactions. So this nucleophilic addition reaction occur in the place of acid catalyst. So we're going to look at them. Then after that, we're going to look at the base catalyzed nucleophilic addition reaction. So let's start with addition of water. So addition of water. So you should know that the carbonic compound, whether it's aldehydes and ketones, react with water in the presence of acid catalyst to produce compound known as gem diol or hydrous. So aldehydes and ketones react with water in place of acid catalyst to produce gemdiol, or other known as hydrous. And the equilibrium, the reversal reaction, so the equilibrium position is shifted much to the carbonyl compound. So that is it. So that's the reaction with water. So we say that aldehydes and ketones react with water in the presence of acid catalyst to produce gemdiol or hydrous. And the equilibrium shifted much to the carbonyl compound, and much to the left hand side of the equilibrium position. So having done that, let's give an example of how this goes. This could be the general structure of aldehydes. That's aldehyde with water, the presence of acid. So we're going to produce a compound that has this nature. So we have the carbon is attached to two hydroxyl group. So that's the way it goes. This compound is called a gemdiol or a hydrate. Example, let me use acetone. Let me use this compound called ethanol. So, or formaldehyde with water, presence of acid. So we have this structure, we have a compound of this nature formed, attaching two hydroxyl group to the carbon of the carbonyl carbon. You see that? Then if I use a ketone, the same ketone had the general formula R linked to another R, 2R linked to the carbonyl group, plus water, presence of acid, give us R, C, O, H, and R. So you see similar kind of compound, hydrous, produced when acids water is added to alkanols. So let's see how this reaction takes place. We're going to use the mechanism of the reaction. We're going to use one alkanol, one aldehyde, and also one ketone. So let's look at example 1. Example 1, let me use maybe an aldehyde, a simple aldehyde to demonstrate this. So this is an aldehyde plus water, giving us this compound. So we have this OH, and then H. So we have a diol produced. So how does the reaction take place? The reaction takes place in 2 steps. So the step 1 is going to be protonation from the acid, the proton, for that's the protonation of the aldehyde or the carbonyl compound. So we now have CH3, C. Remember that the oxygen, as I explained before, has 2 lone pairs of electrons. You can see that, the 2 electrons. So protonation means you're adding a hydrogen ion. That means a proton. That is a hydrogen without any electron. So the protonation of the carbonyl group will occur. So we now have CH3, C, then, and as the protonation takes place, let's see, okay, first of all, they protonate. So this hydrogen ion has no electron. So you're going to bond with this. So this lone pair is used to form a bond with hydrogen atom. So we now have this. And then that. So this is the intermediate formed. Protonation. See, the hydrogen ion has no electron on it. So you're going to share electron, kind of coordinate bonding with the electron from oxygen to form a bond here. That will make the oxygen atom to become deficient, having given electron to hydrogen. So we'll now give the positive charge on the oxygen atom, being deficient electron, having shared the electron with hydrogen. So having done that, second step, or step 2, is attack by the nucleophile. The nucleophile here is water, H2O. Will now attack the protonated aldehyde. So that is the second step in this reaction. So we now have this CH3, this protonated aldehyde having a lone pair on oxygen, then being attacked by water. Water is nucleophile. Remember, on water, oxygen has 2 lone pairs of electron on water. So this electron, this nucleophile, is seeking for a place that is the carbon is electron deficient. So it's going to attack the carbon. As it goes in, this electron pi bond breaks. One of the electrons move to the oxygen. So we now have CH3, C, and then the oxygen become electron rich. Already has 2 electrons. As the pi bond moves to it, it forms another 2 electrons on top of it. And they have this. And then you have water joining here. So we're going to have this water has 2 lone electrons. So one of the electrons used to form a bond. That way it's remaining only 1 now. So one of them have been used to form a bond with carbon. And then you have this produce. So the next step is we're going to have the protonation. The protonation means we're going to remove 1 hydrogen ion from this water. So remove 1 hydrogen ion to form the hydrate or the diol. So remove 1 hydrogen ion, 1 atom. That means let me separate the hydrogen, 1 here and 1 there. Remove 1. One of them goes out. 1 hydrogen ion. An ion going out means it's going to leave without any electron. 2 electrons return back to oxygen. We're going to have CH3 and then C, O, H, O, H, and then H. So that the compound produced. So this compound is called, if I want to name it in chemistry, you open the chain. This is number 1. The function will be zero. Number 1, number 2. So this is now called ethane or ethane because of 2 carbon. 1,1 diol. Ethane 1,1 diol. So that the compound produce ethane 1,1 diol. So having done that, we can still demonstrate this using a ketone. If I use a ketone, by the same process, we see, of course, follow the same mechanism. Ketone, like, let me use this example. Let me use a bigger compound, CH3, CH2, CH3, CH2, CH2. Then let me use this example, maybe perhaps, and then CH3 here. So 2 alkyl groups. This is a ketone. 1, 2, 3 propyl. This is methyl propyl ketone. So with water, it has given us the product. Let me get the product first. OH up, OH down, and then C3. So this compound is called 1, 2, 3, 4, 5. By paper convention, this is 2,2-propane diol. 2,2-propane. Is it propane? No. 1, 2. This is 5. 5 carbon. Pentane diol. Or pentane 2,2 diol produced. So let's see how the reaction takes place, the mechanism. So step 1 is protonation. Protonation, adding proton of the carbonyl carbon. So the carbonyl carbon, that is the carbon having the functional group. So we have CH3, CH2, CH2, then you have that. You're adding a proton to it. And the proton will go to the oxygen. That's electron rich. So that way you're going to find S electron to attach itself. So the electron on the oxygen pulls the proton to itself to form a bond here. The proton has no electrons, so you're going to take this a pair to form a bond, making the oxygen electron deficient. So now I have CH3, CH2, CH2, then C, oxygen, one of the electron used to form a bond, and then CH3. So the oxygen here becomes positively charged, electron deficient, because it has used one of these electron pair to form a bond with hydrogen. You see that produce. The first step. Second step, or step 2, is that this substance react with the nucleophile. So addition of nucleophile. And this time the nucleophile is water. is hydration we're talking about here. So now I have CH3, CH2, CH2, C, we'll bring it down a little, CH3, CH2, CH2, C, then double bond, then plus, there's an electron, CH3 plus water molecule, and in water, oxygen has 2 lone pairs of electron, as we explained. So this, in water, oxygen is rich in electrons, so the oxygen is going to attack a plate you have deficient, that is the carbon center, which should be partially positive in normal case. So, but before it attacks, this electron will be removed to make this carbon electron deficient. So we now have CH3, CH2, CH2, then here we have the oxygen taking back electron from carbon, that is, electron comes back here, it breaks a single bond, then there is hydrogen there, and then the water comes to attach itself using an electron pair. So there are 2 pairs, so one of them used to form a bond, remaining only one, then CH3 produce. So you see that. Let's explain it again. The bond delocalized, goes back to form, now have 2 pairs. There was only 1 pair here before. To make it also electron rich now. Electron rich 2, 4, taking 1 electron here 5, and then 6 complete. And then this water, the oxygen there bring 1 electron from a bond here, remaining 1 electron on the water. So you see that. So in the day, this compound now will now have what's called deprotonation. Water is hydrogen ion is now removed from this. So from this water, you remove 1 hydrogen atom. So 1 hydrogen ion, sorry. And if you do that, the electron here will return back to the oxygen. We're only removing hydrogen ion without any electrons. So we now have CH3, CH2, CH2, COH, OH, and then CH3. So this compound, the same product as we have above, 2,2-pentene-diol. 2,2-pentene-diol. So the same compound as we have above, 2,2-pentene-diol. So you can see that. So this is how hydration or addition of water occur in carbonyl compounds. The next we're going to look at is addition. And as I say, this reaction occurs in the presence of acid catalyst. So we're now going to look at addition of alkanols, which also occur in the presence of acid catalyst. So addition of alkanols. Alkanol can be using ROH. Example, methanol, ethanol, and so on, etc. So that's alkanols. So addition of 1 molecule of an alkanol in the presence of acid catalyst to an aldehyde gives a compound called a hemiacetyl. Gives what's called a hemiacetyl. So what do you mean? Hemiacetyl, and then addition to aldehyde Y to an alkanone, it gives what we call a hemiacetyl. So hemiacetyl and hemiacetyl. So a compound formed when 1 molecule of an alkanol is added to a carbonyl compound, be it to an aldehyde, is called a hemiacetyl. Then if you add it to a ketone, it's called hemiacetyl. Look at the example. If I use an aldehyde, for instance, this is the general form of aldehydes. I'm adding an alkanol. This is represent an alkanol. Maybe let me call it R prime to make this one different from this R. So in the presence of an acid, so acid, this present an acid, having ion shows the presence of acid. So that will give us R C O H and then O R. This is called a hemiacetyl. So the hemiacetyl, the carbonyl compound, the carbonyl carbon is bonded to one hydroxy group, that's OH, and one alkoxy group, OR, alkoxy group. So that is the hemiacetyl. Then if I use a ketone and I add this to it, an alkanol to it, also presence of acid, I have R, C, then here I'll have also the same OH, and then also OR under the other R on this side. See the difference in structure. So this is now called a hemiketal. So a hemiketal has the carbonyl carbon bonded to one hydroxy group and also one alkyl group. But the other end you have under alkyl group, but this one have hydrogen atom because an aldehyde. The white one is a ketone. So addition of one molecule of an alkanol to an aldehyde or will give you a hemiacetyl, while if it's added to a ketone gives us a hemiketal. So let's look at how the reaction mechanism occurs, taking an example of how to form a hemiketal and also how to form a hemiacetyl. So the process is in the same way or follow the same mechanism like addition of water. So let me say, for example, look at this reaction between, let me call this compound, use this compound as example. This compound is called ethanol. Maybe I'm adding methanol to it. It gives me CH3, COH, then OCH3. So giving me an ethanol hemiacetyl, or that is it. So let's see that and see how the reaction occurs, the making of this reaction. So that was the first step of this reaction. Step 1 will also involve protonation, addition of hydrogen ion from the acid used as the catalyst. Protonation of the carbonyl carbon or carbonyl group. Okay. Carbonyl group. So that's right what to use. So you have CH3, CH. Remember what I told you? That the oxygen here must have 2 lone pairs of electron on it. So I'm now adding hydrogen ion to this compound. So having done a reversible reaction anyway. So having done that, hydrogen ion will now move to the place going to find electron because it has no electron. Will now form a protonated aldehyde. We'll have that. So that is it. The oxygen atom now becomes electron deficient, having shared its electron pair with hydrogen. One of the electron pair with hydrogen. So from this. The second step or step 2 is attack by the nucleophile or addition of the nucleophile. In this case, a nucleophile is the alcohol, no longer water. The alcohol, which is methanol, CH3OH. That's our nucleophile. So having done that, we'll now move on. We'll bring this one down. CH3, C double bond, then H plus. This is the nucleophile. I can draw the alkanol to be in this form. This oxygen, I'll focus oxygen that has 2 electrons. Then I'll bring the hydrogen down. I'll bring the methyl group this side. So I can move this to attack the carbon while the electron is being displaced over there. So that will give us CH3, carbon, oxygen will now have 2 lone pairs, and then hydrogen. They now have this one coming in, attaching itself with a bond. So one of the electrons from oxygen used to form a bond. There are two lone pairs, the remaining one lone pair. The next one is the protonation. We'll remove one hydrogen ion. The other ion is then removed. So when it's removed, you now have this CH3. If you remove it, that the electron here now return back to the oxygen to make it complete. You now have CH3, then C, oxygen with the two lone pairs, hydrogen, H here again, oxygen again with the two lone pairs, and then CH3. So you can see this compound are the same. You can see the OH, carbon, OH and carbon, then the methoxy group, then CH3, and the hydrogen on the other side. So that's the mechanism of this reaction taking place involving an alkanol. So the same operation occurs when you use an alkanone to perform this reaction. Okay, let me take another example of using an alkanone. Use an alkanone to do this. Perhaps use an alkanone like CH3, CH2 is a bigger one, CH3. Perhaps I use ethanol, C2H5OH, and alkanol to do this. So write it. I'll have the product CH3, a hemiketal, CH2, C, then OH, OC2H5, and then CH3. That's the product we are going to obtain at the end of the reaction. So let's trace the reaction mechanism and see how it takes place. In the first step, as we said, step 1 is protonation. Protonation of the carbonyl carbon. So you have to protonate the carbon. In the first step, we now have this reactant with a proton. So have this, the proton hydrogen ion. So having done that, remember as we said, the oxygen has two lone pairs on it. So the hydrogen ion which has the electron will now move to this point. We now have a protonated ketone, CH2, then C, oxygen. One of the lone pair used to form a bond with hydrogen. Now have CH3, you know the positive charge. The oxygen having shared electron with hydrogen now become electron deficient, will be positive charge. So having done that, step 2 is addition of the nucleophile. The nucleophile here is ethanol, C2H5OH. We bring this down, CH3, CH2, the carbon linked to OH, the protonated ketone, then CH3. We're now adding this, bring the oxygen atom out with the two lone pairs. See why I did it? They put the hydrogen down and then the C2H5. The same compound as this. Look at it very well. Then the electron from oxygen will now attack the carbon from the ring, while the electron here is displaced to make this oxygen complete. We now have CH3, CH2, carbon, oxygen, the two electrons now complete. We now have this one coming up. We now have this. So what has happened here? The oxygen brought one electron to form a bond here, remaining brought a pair to form a bond there, remaining one pair. So then CH3. The next step is deprotonation, remove the hydrogen ion. One hydrogen is removed. This electron returns back. The hydrogen ion is detached only. Without any electron, so a pair means the electron returns back to the oxygen, making it two pairs at the end of the day. Now CH3, CH2, carbon, then the oxygen with two lone pairs on it, then CH3 on the other side, then oxygen now with two lone pairs being complete. This one resisting and this one coming back to it, and then C2H5. So which you can see right as this compound can be written as C2H5, the same compound C2H5, compress this COH CH3 and also OC2H5. So this compound and this are the same thing. So watch the product and watch this one, they are the same compound. So as we said, when you protonate an aldehyde and when you add alcohol, one molecule of an alcohol to aldehyde, you get a hemiacetal. To a ketone, you get a hemiketal. So having done that, we now look at we are still on addition of alcohols to aldehydes. Then, what of addition of two molecules of aldehydes? Addition of two molecules of alcohols, please. Addition of two molecules of alcohol. So, addition of two molecules of alcohol, one alcohol, to an aldehyde. This time around, we give an acetyl, and for a ketone, it will give a ketal. So how to finish up this? So addition of one molecule, the first we discussed was when you add one molecule. We're still on addition of alcohol. When you add one molecule of alcohol to an aldehyde, you get a hemiacetal. Then to a ketone, you get a hemiketal. But when you add two molecules of alcohol to an aldehyde, you get a full compound called an acetyl. Then when you add two molecules of alcohol to a ketone, you get a ketal. So let's see how it goes. If this is an aldehyde, it's also on the board. And I'm adding two molecules of alcohol to it. So no longer one molecule compared to the previous reaction. With this time around, you're going to get a compound whereby we have this kind of structure. So this compound is now called an acetyl. Look at the difference between acetyl and hemacetyl. In hemacetyl, look at the structure of a hemacetyl. Hemacetyl, one of the groups here is hydroxyl. The other one is an alkoxy group. This is hemiacetyl. But in acetyl, the groups attached to the carbon are two alkoxy groups. But here, one group is alkoxy, one is hydroxyl for the hemiacetyl. See the difference? Then, if you use a ketone in the reaction, using two molecules of an alcohol, you get R, C, also OR, OR. The structure look alike, are they not? They look alike, except that for the aldehyde, the end, the terminal atom here is hydrogen. For the ketone, the terminal atom here is now K group, R group, as you have in the structure. So this one now is called a ketal. So a hemiacetal, an acetyl is the compound from acetyl when two molecules of alkoxy group is added to an aldehyde. While a hemiacetal, hemi, is a compound from when one molecule of an alcohol is added to an aldehyde. Then a ketal is a compound from when two molecules of an alcohol is added to a ketone. While a hemiketal is a compound from when molecule of an alcohol is added to a ketone. See the difference? So we're now going to look at the mechanism of formation of acetyl and acetyl and ketal. So let's start with acetyl. For example, let's write a reaction. They use a longer okay, this one is called propanal by convention. Propanal. So propion aldehyde. So we now have perhaps we're adding two molecules of, let's say, methanol to it. We produce the product of this nature, CH3, CH2, whereby on top of this we're going to have the methoxy group, that is the methoxy from that canal. So that is it. Given a compound by upper convention, that compound would be called 1,1,dimethoxypropane, because this is number 1. Number 2, number 3, propane, 3 carbon. Then this is the number 1, 1,1-dimethoxy. This group is called methoxypropane. So let's look at the reaction mechanism, how this reaction takes place to give us the acetyl. So before we go to the acetyl, the first thing you have to do is you have to first of all get the structure of the hemiacetyl formed. The hemiacetyl formed by this reaction. You have done that, you can do the mechanism yourself, but you can still get the structure without waste of time. Hemiacetyl will look like this: CH2. Then this one will carry OH. While one will carry the OH. This is the hemiacetyl produced. So the mechanism start with the hemiacetyl. That is, it start with the protonation of the hemiacetyl. So that's where the reaction starts from. So the mechanism, step 1, is protonation of the hemiacetyl formed in the first stage. So you have the compound CH3, CH2, COH. So we're going to protonate this compound, proton without any electron. Remember that this also is electron rich. So we're protonating the hydroxy group. We're going to have CH3, CH2, carbon. Then you have that. So the oxygen of the hydroxy group will use 1 electron to form a bond with hydrogen coming from the proton. And this is the other hydrogen there. And there's also a lone pair. This becomes positive charge because the oxygen has used this electron to share with the hydrogen, becomes electron deficient. So we have a protonated hemiacetyl. So when this is formed, the next thing is elimination process. What is eliminated? Elimination process. So, but mind you, before we go on, that this oxygen also contains 2 lone pairs of electron in it. So elimination of water, reaction reversible, please. At the next stage, water eliminated. So we're going to pull off water. So this is water, H2O. You pull away the 2 electrons, you share with carbon. That will make this carbon become deficient electron. So to compensate for the electron loss by the carbon, this electron that is in oxygen will now move again to form a double bond here. So you see the way it goes. So we now have this CH3, CH2, water is lost, minus water on top. Then carbon, hydrogen, double bond, then CH3. So this place has a double bond. So this is formed, but that is not the final product obtained. Then we go to the second stage, or step 2. Step 2 will now involve the attack by the nucleophile, which is a methanol. So the step 2 is attack by the methanol, the nucleophile, which is the reactant here. So you now get up that intermediate form there: CH3, CH2, C, double bond, oxygen, and then CH3, and then hydrogen. Before we continue, you should know that this oxygen here is positive charged because it has shared electron. I think give electron to carbon, it becomes deficient. So there's a positive charge on this oxygen. Then plus this, which is, we can draw it like this. The oxygen, bring the oxygen out. It has 2 lone pairs of electron, hydrogen, and then CH3. This is the methanol, the same thing. So this compound will now, this molecule will now look for a place that's electron deficient, going to attack the carbon. You're going to attack the carbon there. So, and at the same time, the electron, to make this oxygen become deficient electron, the electron here will return back to oxygen. You can see that. So we now have this CH3, CH2, C, H, and then the other thing here becomes electron rich. Now we're having two pairs again, two lone pairs return back to it, or a pair return back to make it two lone pairs. Then this one attached itself, you have O, then H, C, H3 with a lone pair, because remember that it has two lone pairs, so you're going to use one to form a bond with this carbon. And having done that, since I use one to form a bond with this carbon, that means this oxygen now becomes electron deficient. It has only one pair remaining, that give it positive charge because it's now deficient in electron, having lost electron. Or invariably, you can say use electron to form a bond with carbon. So having done that, the next stage is proton loss. That's the final stage. The proton is lost from this. So you remove a proton. Proton means remove only hydrogen, while the electron here return back to us to make it complete, to make it two lone pairs. So now have CH3, CH2, then carbon, and then oxygen, having two lone pairs now. Remember the lone pair exists here, and then this one is the bond coming back to it. A bond means two electrons. So you now have that, then CH3, hydrogen, and then under have also the same oxygen with two lone pairs, and then CH3. Look at this compound and this compound, they are the same thing, CH3, CH2, or C2H5, which is this carbon bonded to two alcohol methyl group, OCH3, OCH3 up, and then hydrogen down, giving you the acetyl produced in this reaction. So you can see that. So having done that, we now take another example. Example we want to take is how we can form a ketyl. In the ketyl formation now, we're considering reaction between a ketone and two molecules of an alkanol. Let's say ketone, like, let's look at this example, acetone is a ketone. Acetone, or you can call it propanone, plus two molecules of, let's use ethanol in this case, to form a ketyl. So for a ketyl, we're going to have this structure, CH3, and it's acid catalyzed, as you know. This is indicated of acid. Then C2H5 here, OC2H5 there, and then CH3. So this is a ketyl produced in this reaction. So having done that, our interest now is to show the reaction mechanism, how this is formed. So it occurs in two steps. So the step one, just like in the formation of acetyl, is protonation of the hemiketyl. We're going to do first, we'll get the sort of the hemiketyl form before we now go to ketyl formation. Hemiketyl, as I've been taught, will look like this. We have we did it a few minutes ago. We have hydroxy group here, and then have this group, the alkoxy group down. This is the hemiketyl. So produced. There's a difference between hemiketyl and ketyl. Ketyl has two alkoxy group on the carbon, while hemiketyl has one hydroxy group and one alkoxy group. Please, this place is CH3. If not, it would have been called a hemiacetyl. So that is it, CH3, CH3. So the first step is protonation of hemiketyl. So we have CH3, C, OH, OC2H5. Remember, the oxygen atoms have two lone pairs of electrons on each, both that one on OH and the one on the methyl group. So when I'm protonating, adding hydrogen ion, protonation occurs on the hydroxy group. So this hydrogen ion moves to one of the lone pair, giving us CH3, C, then O. You can put it here if you wish. And then, because this has lost one of its electrons, or have used it to bond, not actually lost, it becomes positively charged, electron efficient. Then CH3, and then here O, then C2H5. The next step involves, remember, is reversible processes. Involves loss of water. Measure water. So remove water here, minus water. And this is water, indicating water. So this will also pull away the two electrons. So while one of the electron lone pair will return to make this carbon complete. We now have CH3, CH3, and then double bond here because this forms a bond. A pair means a bond. And then O, C2H5. And then since the oxygen has given its electron away, it doesn't become electron deficient, positively charged. So the step two now will involve, what I call it, will now involve the addition of the nucleophile. So addition of nucleophile, which is the ethanol. The nucleophile is the ethanol, the other reagent. So that's the second step involved in this reaction. So now this will come down, CH3, CH3, then a bond, double bond, then C2, adding the nucleophile. Nucleophile is bring out oxygen. So it's very easy for you to understand. The oxygen atom with two lone pairs, bring the hydrogen down, and move the AT group on the other side. So the nucleophile, the oxygen atom will go to electron, move to the carbon, which should be electron deficient. And then when this happens, remember this carbon should return, if this electron here returns back to oxygen, so we'll take this one electron or one of the bonds to an oxygen to make this carbon electron deficient. So the two occur simultaneously. So we now have CH3, C, the oxygen here now has 6 electrons. Remember that before it had, look at it here. Okay, before one would had only one electron, only a pair of electrons. When this electron returns to this point, we have only one remaining out of the two. So there's only a pair remaining here now. And this time around, we're returning the pair back to it to give it back, give it 2 pairs. Okay, and then we can put H here and C2H5 over there also. So that is it. Then this one comes to bond here. We now have oxygen. It has 2 pairs, so use 1 pair to bond, remaining only 1 pair here. So let me use a sharper marker. So there are 2 pairs, so use a pair to form a bond here, remaining only 1 pair. And then we have hydrogen, can put it here, and then C2H5 can put it here. And then on this side you have CH3. So having done that, look at this structure. And of course, this oxygen, let's see, it has 2 lone pairs and use 1 to form a bond, remaining 1. So this also becomes deficient. Put a positive charge on it. So to form a bond, so put a positive charge whenever the atom loses an electron to use this electron to form another bond with another atom. So that means it appears to have lost electron, now give a positive charge. So having done that, the next step is the protonation. Remove 1 hydrogen ion from this one. This hydrogen ion being removed. Then the electron returns back to us to make it 2. Because normally in neutral state, also we carry 2 pairs. So we now have CH3, carbon, also in the middle having 2 lone pairs, and then C2H5, CH3, and then there's something missing here that we do not do very well. We want to find out where the error is from. This is C2H5, okay? Let's go back. This OC, so okay, that is where from here. C2H5, yeah. OC2H5, yes. So yeah, there's no hydrogen here, the error. So this is OC2H5. So yeah, it should be no hydrogen should be there. C2H5. No hydrogen, please. So that is correct now. We have O, then C2H5. Look at this structure we have obtained here and this structure. They are the same compound, hemiketide. So we can name this compound. This is number 1, number 2, number 3, one any end. Give you the substituent group 1, 2, 3, 1, 2, 3. So this is 2,2 dimet. This is et from ethyl. So 2,2 diethoxy 1, 2, 3. Then propane. So you see that being formed. So we are seeing how to obtain hemiacetyl, hemiketide, and acetyl and ketide there. So the reactions, the complete reactions of what I call it, of carbonic compounds, aldehydes and ketones involving acid catalyst. We now look at the third reaction, which is addition of hydrogen cyanide. This reaction does not occur in the presence of acid. No, unlike hydration, the addition of water, and addition of alkanols that take place in the presence of a small acid or the strong acid in trace amount. But this reaction doesn't occur in the presence of acid, it's not acid catalyzed. So it occurs in the presence of little dilute alkali. So it doesn't occur in the presence of acid. The alkali, first of all, reacts with the hydrogen cyanide to produce large concentration of cyanide ion, which functions as a nucleophile. So that's what happens first before the reaction commences. So the hydrogen cyanide, which is HCN, will react with hydroxyl. This hydroxyl indicates the presence of base or alkali. So you can draw the hydrogen cyanide structure. There's a single bond between hydrogen and the carbon here. In the process, the cyanide ion pulls away the 2 electrons, a kind of electrolytic fission, to give you cyanide ion, which is negatively charged, pulling away 2 electrons. Then this hydrogen ion, a proton, goes to the giving us water. Right? So we produce the nucleophile that is used in the reaction. So let's go straight to an example of this reaction. This is an aldehyde or ketone. When we use an aldehyde, we produce what we call an aldehyde cyanohydrine. And when we use a ketone, we produce what we call a ketocyanohydrine. So in both cases. So let's use an aldehyde for instance. Like I use CH3, CH is an aldehyde. Okay, CHO, there is this one, ethanol or acetaldehyde with hydrogen cyanide. The product is very simple to understand. Let me put the OH on top. Doesn't matter anyway where you put it. The hydrogen it will now move to the oxygen, which is breaking the bond here, and the cyanide coming down. So that they have the nature of the product. So if I use a ketone for the process, this one called propanone. So hydrogen cyanide, the same kind of product, CH3. So OH bond broken, and then CN, and then CH3. So this is now called a cyanohydrine. Aldehyde is from aldehyde, so called the aldehyde cyanohydrine ketone cyanohydrine. So let's see how this reaction takes place. Can use one example. Anyhow, the same step you apply for this, the same step you apply for the other one. So we mustn't use the 2 compounds. So it's the same process. The important thing is to understand the mechanism of this reaction. then you can do it yourself. So let me use one aldehyde or ketone, anyone that comes to my mind as I'm moved. So let me use this one, CH3, CH2, and then look at this. This is an aldehyde. Good. And this aldehyde, you should know how to name it. Nomenclature. This aldehyde is called, the 3 carbon biopack conversion is called propanal or propion aldehyde by common nomenclature. So the first step one, okay, let's write the equation first and then move the mechanism to confirm our answer. CH3, CH2, the hydrogen goes to the oxygen to break the bond, and then the cyanide ion goes under. So now I have the other compound, we can call it, this is 1, 2, 3 biopack nomenclature, we can call it 1 cyano, this is 3 carbon, propane, propanol, propanol. So let's see how it goes. Now in the first stage, or step 1, I have an attack on the carbonyl carbon by the cyanide ion. So the cyanide ion will attack the carbonyl carbon. So how this structure the reaction CH3, CH2. Remember that this carbon has 2 lone pairs. Don't forget that. This oxygen has 2 lone pairs, please. And the cyanide ion is also an each is electrophile. It has a lone pair. So you cannot go to oxygen because it's already rich. So you're going to go to a place that should be electron deficient, which is the carbon. As it goes there, to make the carbon electron, the electron here will shift to oxygen to make the carbon electron deficient. So we now have this produce CH3, CH2, C oxygen, double bond, and then double, make this one negative, and then hydrogen, the center ion comes here, Cn. So that is it. You see what is happening. So this one comes in, the one shifts to make the oxygen more electronic because it's now having excess electron, negative charge. So that's the first step of this reaction. Then the second step will now involve attack the protonation, or step 2, which is protonation, adding of hydrogen ion. Protonation of this ion produced our CH3, CH2, C. They have to understand this. So I have Cn. We're adding a proton, which is hydrogen ion. Where is the hydrogen ion from? From the hydrogen cyanide. So the proton is electron deficient. That's electron. So going to attack or bond itself to one of the lone pair of oxygen. So you now have CH3, CH2, then we have a OH. So one of the electron pairs, there are 3 electron pairs, 1, 2, 3. All of them used to form a bond with oxygen, making it 2 electron pair remaining now. Then cyanide, so hydrogen. So you see, look at this compound and this other one are the same thing. So you can try it using a ketone. Also, similar processes involved. You get similar kind of product, just a little difference in their structure. So we are seeing the third reaction, which is reaction with addition of hydrogen cyanide. The third reaction we want to look at is, or the fourth one is addition of sodium bisulfate, which is of course called sodium hydrogen triosulfate 4 in IUPAC nomenclature. Sodium bisulfate or sodium hydrogen triosulfate 4. Now, in the reaction of carbonic compound, whether it's aldehyde or ketone with such compound, it leads to the production of a crystalline solid. A crystalline solid which is soluble in water. So both aldehydes and ketones react with this compound to produce a crystalline solid which is soluble in water. So a bisulfate compound which is soluble in water. So how does the reaction take place? This compound, sodium bisulfate, first of all, ionize in water to produce, or in aqueous solution, give us sodium ion and hydrogen sulfate ion. The hydrogen sulfide ion will later ionize to give us hydrogen ion and then the triazosulfate 4 ion. So this will now function as our nucleophile in the reaction, in addition to either an aldehyde or to a ketone. So let me use one example, either an aldehyde or ketone, to illustrate this. Okay, let's use a ketone. For instance, let's use this ketone, CH3, and then that's this ketone. So plot this. So the first step, which is step 1 now, is addition of the nucleophile, which is the triazosulfate 4 ion, or the triazosulfate 4 ion. So, or the sulfite ion. So when this ion comes in, it's negative charge. So it's bound to attack the carbon atom, but that this oxygen has 2 lone pairs on it already. So when it comes, this electron is placed to oxygen to make this electron deficient. So we now have a CH3, carbon, then oxygen now becomes more electronegative, negatively charged, CH3, and then the triazosulfate ion attaches itself, also having a negative charge. So that is the initial reaction state that takes place, and this reaction is reversible, as you said. Always, please put a sign. Then the next step is protonation. Protonation will now take place. Hydrogen ion comes in. Where we attack, we're going to attack the oxygen that is rich in electron. So it moves to this point to form a bond with one of the lone pairs of oxygen. We now have CH3, COH. Remaining 2 lone pairs, since we have 3 lone pairs on the negative ion. So we now have SO3 down, then CH3. So having done that, so that would have been the product, but later on also we're going to add sodium ion. The addition of sodium ion is reversible. So addition of sodium ion is reversible, and then the sodium ion is positive charge is going to attack the negative triazosulfate ion. That gives us CH3. Here C, O, H, and then CH3, and then we have this bisulfate compound from SO3 Na produced, which we said is white and crystalline in nature. So bisulfate compound produced in the reaction. So this reaction can take place whether the compound is an aldehyde or whether the compound is a ketone or an aldehyde. The same process will occur. So having done that, we look at the 5th reaction, which is addition of Grignard reagent. Addition of Grignard reagent. So Grignard reagent is an organometallic compound that was developed by one of the simplest organometallic compound that was developed by Grignard years back. So it's produced by reacting an alkyl halide. An alkyl halide, this is alkyl, this is a halogen with magnesium metal. So when you react coupling an alkyl halide with magnesium metal give you the Grignard reagent. We now have just this structure. So this is the Grignard reagent. For example, I can use methyl as my alkyl group, and then chlorine as my S, chloro plus magnesium. That gives me CH3 MgCl. So this is the Grignard reagent. So you can still use any other maybe ethyl. Let me change the alkyl group. So they not be acid or an iodine, an alkyl group, and a halogen. With the magnesium is the metal that you use, no other metal. So the metal I use is magnesium, not calcium or any other metal, not sodium. So you now have this. This is also a special Grignard reagent. So let's see how Grignard reagents are added to carbonic compounds, the kind of product we should expect. Now, if you look at this Grignard reagent, before we continue, we'll split the compound into two, or we'll give it polarity. The methyl group or the alkyl will give negative polarity, while the halide group is giving positive polarity. Also here, the ethyl group is or alkyl will give negative polarity, while the magnesium iodide is giving positive polarity. So in addition, reaction of carbonic compounds to a Grignard reagent of carbonic compounds, that's the way we move it. We give the alkyl group negative, and the negative one will now attack the carbon of the carbonyl group, while the positive will attack the oxygen atom, which is electronegative. So let's take an example, whether it's a ketone or an aldehyde. So if I use a ketone, for example, let me this one. So I can use any ketone. The process remains the same thing. The mechanism is somehow on multiple players at the same time. So let me use a Grignard reagent like, let me use this one. Yeah, use this one for the reaction. So here is negative, this point is positive. So remember that oxygen has two lone pairs of electron on it, making it chiefly or mainly electronegative. So the positive part of the molecule will now attack the oxygen. The negative part of the molecule will now attack the carbon. And this carbon makes it electron deficient. The electron from the that form the pi bond will return back to oxygen. So we have that. So we now produce CH3, CH2, then carbon, the bond is broken here. One of the electrons will be used to form a bond with this molecule, which is with this part, which is MgCl. So since remaining two, so if this electron used to form the bond, this pair, it meant this one and the one that is coming back to this oxygen. So, and then this place, this one will not take the word CH3, the alkyl group, and then have another alkyl group beside CH3. So that the intermediate product formed, or the product formed in the reaction. And then if this substance is then hydrolyzed in water in the presence of an acid, hydrolyzed in water with acid will produce an alcohol. An alcohol whereby we're going to have CH3, CH2, C, then O, H, CH3, CH3. So this group is replaced by a hydroxy group in hydrolysis. So this is a 3rd-degree alcohol or tertiary alcohol. So what am I trying to say? What we're saying here is that if Grignard reagent is added to a ketone, an alkanone ketone, and the product is hydrolyzed in water, you're going to produce a 3rd-degree alkanone. Why is it called 3rd-degree? Look at the central carbon, the carbon having the hydroxy group. It has 3 different alkyl groups. This is methyl, and ethyl. You can compress. There is C2H5. 3 alkyl groups on the central carbon makes it 3rd-degree alkanol. So when ketones are hydrolyzed in water, when ketones react with Grignard reagent and the product is hydrolyzed in water in place of acid, you're going to get a 3rd-degree alkanol. No matter the kind of ketone you use, the product will be a 3rd-degree alkanol. The question is, what if the compound is an aldehyde? If it's an aldehyde, are we going to get a 3rd-degree alkanol? That's the question we're going to ask ourselves. No. If the compound is an aldehyde, we'll not get a 3rd-degree alkanol. We're going to get a 2-degree or secondary alkanol. Let's see why it is so. Let me use an aldehyde in this case now. So an aldehyde, maybe I'll call here, this is carbon. This means an aldehyde. Good. Look at the hydrogen at the end. If I have an alkyl group here, would have been a ketone, as we explained. So let's say with CH3, the same kind of a reagent, whether it's this reagent or let me use another one, let me use iodine here. Green reagent. So this part is positive, this part is negative. And this oxygen has two lone pairs of electron here. So having done that, so this one attacks this carbon and the electron here returns back to oxygen, while the positive end attack the oxygen. So we now have CH3, CH2, then carbon, then oxygen here forms the bond with magnesium iodide. So electron remaining now because one have been used to form a bond, then remaining this one, and this one comes out to form another bond. So have hydrogen, then this part you have CH3 attached. So hydrolyzing water in the presence of an acid, this group turns to hydroxy group. We now have CH3, CH2, COH, CH3, and then H. This is a secondary alkanol. Why is it secondary? Because the carbon bearing the hydroxy group have only two. This is an alkyl group. This is alkyl, but this is not an alkyl group. So have two alkyl groups bonded to the carbon of the hydroxy group. That gives you a secondary or 2-degree alkanol. Of course, this compound is butan 2 or 2-degree alkanol produced. So secondary aldehydes give us secondary alkanol when they react with green reagent and the product is hydrolyzed in water, while ketones give us tertiary alkanols when the product is hydrolyzed in water. The only alkanol that gives us primary among the aldehydes, as I said, aldehydes gives us secondary alkanols when they react with green reagent. But the exemption, the only aldehyde that gives us primary alkanol is methanol, otherwise known as formaldehyde. Methanol is the only alkanol, the first member of the common alkanals that gives us a primary alkanol. So let's see how it goes with the same reagent. So it gives us primary, doesn't give us secondary. Other aldehydes will give us secondary alkanol, but methanol give us primary. So let's see how it goes. So this we have this. So this one attacks the carbon here, while this part attacks the oxygen. Electron is being displaced. So we have HC. The oxygen forms a bond with the metallic halide. We have this. While this one comes down here, we have this. So when hydrolyzed in water, in the presence of an acid, this group is removed and replaced by OH. We now have H, C, H, CH3, and then OH. This compound is primary alkanol. You see the hydroxy group that makes the compound alkanol bonded. The only alkyl group here is this methyl, only one methyl group. So this is ethanol. It's a primary or 1-degree alkanol. So you see that, you understand the reaction between carbonic compounds and Grignard reagent. So we're now going to addition elimination reaction. So move on to addition elimination reactions, elimination reactions of carbonyl compounds. So these reactions involve the addition of a nucleophile followed by the elimination of water or other small molecules. Examples, one of these reactions include reaction with ammonia and amines. The amines here include the primary amine and secondary amine. Two, reaction with hydrazine and hydrazine related compounds, just like hydroxyamine, semicarbazine, phenylhydrazine, and so on. Then the third one is the one called Wittig reaction. So these are the reactions that aldehydes and ketones undergo that involve addition of a nucleophile first, and then next will now be elimination of water or other smaller molecules. So we're going to start with addition or reaction with ammonia and amines. So aldehydes and ketones react with ammonia to form compounds known as imines. I repeat myself. Aldehydes and ketones react with ammonia to form imines. What are imines? An imine is a compound that has a double bond between a carbon atom and a nitrogen atom. So an imine is a compound that has a double bond existing between a carbon atom and a hydrogen atom. We call such compounds imines. So let me take an example. I can use a ketone, I can use an aldehyde to do that. So you'll probably use the ketone to demonstrate a step. So let's say the first step. Let's look at the reaction first. Let's draw this, use the ketone, a name ketone. Let me say acetone plus ammonia. So let's see how the reaction goes. So the first step, or step one, is going to be addition of the ammonia. Addition of ammonia being a nucleophile. In ammonia, there is a lone pair of electron on nitrogen atom. So in this reaction, we can have this ketone. Remember, in the oxygen atom of ketone, there are two lone pairs of electron. And then the imine ammonia. For the ammonia, we're going to extract the amino group, NH2, and then from the hydrogen. You can see the way I wrote ammonia. And you have a lone pair of electron on the amino group. Now in this reaction now, the amino group will now, or the whole ammonia molecule, of course, will now attack a place where you have a deficiency, which is the carbon center, because oxygen is already rich in electron. So it comes into that point to attack that nitrogen, that carbon atom. And at the same point, for this ammonia to enter here, this bond should be delocalized. So you're going to display this bond to the oxygen. So now have CH3. Then oxygen now will now have 6 lone electrons, making it having excess electron rich, negatively charged. Then has CH3. Then the ammonia molecule fusing itself here. Remember that ammonia form a bond by bringing its electron to share with carbon. That makes the nitrogen atom become positively charged. So that the first intermediate produced in the reaction, as you have there. Then the next step we're going to have now will now be going to have a proton loss. So we have the proton loss, the protonation going to take place. So, or proton transfer taking place. So we're going to have proton transfer. Reversible process, please. Proton transfer. Where is the proton coming from? Coming from the ammonia is transferred to the oxygen that is up. While the electron is giving back to Mr. Nitrogen. Giving back to nitrogen. So you see that. The proton goes to the oxygen up. So you now have CH3, COH. The oxygen now is having two lone pairs certified. Then CH3. Then the nitrogen will now, what remains here is the amino group, NH2. Then the lone pair of electron, which the hydrogen left behind, returns to the nitrogen to have that molecule formed. Then we'll now go to step 2 of the reaction. In step 2 of the reaction, what's going to happen in step 2? In step 2 of the reaction, we're going to have protonation, or step 2 will involve protonation and a proton of the hydroxy group, the OH group. the hydroxyl group, you can see it here. So we're going to protonate it. Because after protonation, the next thing that will happen is elimination of water molecule. So bring the substance up here. CH3, C, have the electron, then protonation will occur. I can open this one up as I wish, okay? Wow. So have it, protonation of the hydroxyl group. So the proton goes to the oxygen to protonate the oxygen atom of the hydroxyl group. And that's the first step, is a fast reaction. So it's a fast reaction. So having done that, when I have CH3, C, so one of the electron from the oxygen will be used to form a bond with the oxygen, meaning only a pair. There were two pairs before. So one pair used to form a bond with hydrogen, sorry, not oxygen. And that made the oxygen atom here become electron deficient, positively charged. Then CH3, and then NH2. So you can see this. So when this is produced, the next is elimination process now. Elimination process is we're going to remove water molecule. The water molecule is what we are seeing up there. So it's been eliminated. It takes away the two electrons. And then formation of the double bond will also occur here. The elimination process occur with double bond formation. The electron pair from this amino group will move to the carbon to complete its state. So now have CH3, C, and then CH3, double bond formed here. This amino group, of the nitrogen has given the electron to carbon. That means this nitrogen to become electron with positive charge, electron deficient, because they are giving the electron to carbon. So having done that, the last step in this reaction now will now involve removal of a proton, remove hydrogen ion from the amino group. So this is the amino group. So you can open, there are two hydrogen atoms here, so you can open it up, H and H. So we want to remove a proton. A proton means you are attracting only one hydrogen atom without any electron. The electron here returns back to the nitrogen. We now have CH3, C, CH3, double bond, NH, and then the lone pair given back to it. So this molecule form is called an imine. Has a bond formed between carbon and two nitrogen atoms. So imine formed from ammonia are rather unstable and normally undergo polymerization reaction to form higher compounds. So this is a reaction of either you can use a ketone or you can use an aldehyde, the way it goes with ammonia, how the reaction takes place. Now, let us now use an alkyl, use amine. So with amines, so reaction with amines. Let me say with primary amines. Primary amines. So with the first we did was with ammonia. Reaction with ammonia. So that we are still under addition elimination reaction. The first we did was reaction with ammonia. So we're now going to amines. We're choosing primary amines for this demonstration. Now, what's the primary amine? If you look at ammonia, it's very simple. Remove one hydrogen from ammonia and bring in an alkyl group to place hydrogen is now called the primary amine. So this is primary amine, PA, primary amine. Remove another hydrogen or remove two hydrogen and bring in two alkyl groups. This is now called secondary amine. Okay, so you understand the structure of what I mean by primary amine, what I mean by secondary amine. Example, if I use methyl, CH3, you see, this is a methyl amine, is a primary because I have one alkyl group and amino group. If I have CH3, NH, dimethylamine is a secondary amine. So you have to understand what is meant by amine and then primary amine. So our focus here is on primary amine. So let's see how primary amines react with a carbonyl compound. In this case, I'm choosing an aldehyde, which is an aldehyde. So you can still use a ketone. So with the primary amine, like let me use CH3 methylamine. I can still use ethylamine. Ethylamine is this, or CH3 CH2 NH2. This compound are the same. Compress this, you're getting that back. So this is any of these can the same mechanism will follow for will be observed for this or that, because they're all primary amines with either an aldehyde or a ketone. So step one, you're going to be attack or addition by the amine. So primary amine. So we're going to observe similar step as we observed in addition of ammonia. Similar reaction or similar step will still take place with ammonia and this one, similar reaction. So we now have CH3, C double bond. Remember that on this double bond, we are having 2 lone pairs of electron on oxygen atom. Don't forget that. Always bear that in mind. Then the amino group, we'll put this one first because that the one, the lone pair is on nitrogen atom, just like in ammonia. So this will move to attack this carbon. The electron will move to this carbon, while this electron will delocalize. So we now have reversible process, CH3. Then the oxygen becomes negatively charged, now having 6 lone pairs, negative. And then you have this, and then you have this one coming in. The amino group will introduce its electron to bond carbon. So that since the nitrogen share electron to carbon, as it becomes deficient, positively charged here, from there. So next step, we're going to be a proton transfer, as we did in the ammonia, proton transfer. So one of the hydrogen atoms will move from the amino group to this. So I can open this up in this way, draw it like this, bring hydrogen down. There are 2 hydrogen atoms, good. And then put my positive charge. You see the same thing. So the proton here now moves to the oxygen without any electron, while electron return back to nitrogen. You can see what is happening there. So we now have CH3, then C. So when the hydrogen ion without electron goes, it forms a bond with one of the electrons there, one of the lone pairs there. You can see that the oxygen now become complete with the normal way of having 2 lone pairs. They have hydrogen, and then here we now have N, and then hydrogen, ammonia, and then this hydrogen now, nitrogen now atom now collect the 2 lone pairs of electron, which the hydrogen abandoned, so goes back to the nitrogen. So we have this intermediate form. That is the first step of the reaction. So having done the first step of the reaction, now go to the second step of the reaction, or the second stage of the reaction, which continues with protonation of this intermediate. So step 2 is now protonation. We take place protonation and subsequent loss of water. So we have go because there are many steps here. So let's write this first. You know, only protonation will take place, and also water loss of water will also take place. So, and also deprotonation, about 3 steps will occur in this second stage. So we have this protonation, adding ion. Without protonation, we cannot be able to move water. Protonation is a very fast process. So this goes to the hydroxyl to protonate the hydroxyl. So this electron is the one drawing this place. That's the way it should go. Electron draws positive. So having done that, we'll have CH3, C, and then oxygen, bond, and then hydrogen again, hydrogen, CH3. So we have that produced. And remember that the oxygen, the electron that is shared with this hydrogen ion that brought nothing, that made this oxygen atom become positively charged. So the next stage is then loss of water taking place there. Loss of water taking place. I think there are errors somewhere. This is the compound we're using. So, okay, here should be nitrogen, a lone pair. That's what we have. We'll carry it over to the side. And that should be the right thing. Cutting it now. We now have this. Okay. We have that. Produce. Okay. So we'll now move on. So loss of water, as I told you, the loss of water is accompanied by, so the water is removed or by it to pull away the two electrons to make the oxygen to have two lone pairs. And then this electron here on nitrogen will return to this place to form a double bond. So to form an imine. So the two processes occur, the water loss and the delocalization of the lone pair to form a double bond here occur at the same time, as we observe in ammonia. So now have CH3 and then have C, H, then double bond produced here, and then N, well then CH3, and then hydrogen atom, so double bond. And this nitrogen has given this electron away to carbon. That made the nitrogen become positive charge. So you can see that. So the process critically and look at it very well. We'll now go to the last stage now, or not the last stage, the one more operation. The one more operation is that this will lose a proton. Deprotonation. We're going to lose a proton to give you the final proton, an imine, sorry. So let's see the last operation. This will lose the deprotonation, a proton from this. The hydrogen ion leaves completely while the electron returns back to nitrogen. I have CH3, then CH, double bond here, then we have a lone pair going back to this nitrogen, and then the hydrogen atom have been removed as a proton and an ion, so it has gone off. That becomes our imine, the final product. It's the more stable imine produced, unlike that of ammonia. So this is a product obtained. So we can say write this product in this form: CH3, carbon, link the double bond with nitrogen. You see the same thing? You see this hydrogen is bonded to this carbon, can put it on top of the carbon. You see that it's the same compound as this. You produce an imine in the process. So you see, these are the reaction takes place. So having done that, we're now going to the second addition elimination reaction. We're seeing the first one, which is addition of reaction with hydrazine and hydrazine related compounds. So we'll look at the reaction with hydrazine and hydrazine related compounds. Another addition elimination reaction that involves carbonyl compounds. So you can see the carbonyl functional group that represents either an aldehyde or a ketone. If I have two alkyl groups here, R, it becomes a ketone. You have an alkyl group, R, and a hydrogen atom here becomes an aldehyde. Then this compound represents a hydrazine derivative. The compound hydrazine is NH2, NH2. This is hydrazine. So if I put under NH2 here, that becomes hydrazine. But we'll say that hydrazine or hydrazine substituted compound. So I can replace this NH2 with another group. So this reaction is a reaction that involves hydrazine or compounds that have hydrazine nature, whereby one of the amino group replaced by another group. So this reaction is just like a simple condensation reaction, whereby the hydrogen atom from one of the amino group here, that's H2, pulls oxygen to give you water. And then the carbon, double bond, couples with the NZ. You can see the product here. whereby the oxygen goes with hydrogen and then the nitrogen and the other group is joined to the carbon to give you the final product. Now, hydrazine compound, one will have, as I said here, let's focus on this. Then, if Z is NH2, if you replace this Z with NH2, that we're going to have this. Replacing Z with NH2, we'll have this. That is our hydrazine. Is Z replaced with OH, the hydroxy group? Is Z replaced with OH? That means here going to be OH at our product. So if you replace Z with OH, as we have here, we have what's called hydroxylamine. Then if you replace Z with this group, which is NH6CH5, replacing Z with N or whether here or there, with NH6CH5, we have this compound H2N, then Z becomes NH6CH5. This is called phenyl-hydrazine. Okay, then if Z is this group that has a benzene ring and some substance on it, replace Z here with this group. You can see that. So you can see NH2 coupled with the whole of this group, NH, everything together now. It's now called 2,4. That is number 1, 2, 3, 4. 2,4-dinitrophenylhydrazine. So if you replace Z with this other group, let's bring it up. If Z is this NHCONH2, then this group that is involved in the reaction, replacing Z with this, will now become H2N NHCON. This group, this is now called semi-carbazine. 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 So all these substances we mentioned, either you use the hydrazine when you have NH2, NH2 there, or hydroxyamine when you replace Z with OH, or phenyl-hydrazine when you replace Z with NH6CH5, or you have carbazine when you replace Z with NHCONH2. All this reaction will give you the kind of product where Z stands for the substance that you're going to have, which you mentioned already, and they all follow addition elimination mechanism. So we're going to look at this reaction mechanism one by one. We're going to start with reaction with hydrazine. With hydrazine, we look at the reaction mechanism. So with hydrazine, we can pick either a ketone or an aldehyde. This is a hydrazine, NH2, NH2, a single bond here. I will form a product. The product we're going to form will look like this. We'll have a CH3, bracket 2, C. Then, of course, as I said, water is eliminated. So double bond will come in. NOH. So if you look at it, the peak hydrogen here, and nothing that goes off. We'll now have CH3. This one will now be eliminated as water. Water is removed. So you eliminate this and that. So you now have carbon and methyl group 2 times. They have carbon, double bond, then linked to nitrogen, and then NH2, not OH, NH2 here. So that is the product formed in this reaction. So we normally call that product a hydrazone. A hydrazone, since we use a ketone here, a ketone, we'll now call it ketone hydrazone. And the ketone we're using here is acetone, we call it acetone hydrazone. So that's the compound formed. Now let's look at the mechanism of this reaction, how it occurs. So look at the first step. The reaction is similar to what we studied under ammonia and amines. The first step we're going to be the addition of the hydrazine That's the first step of the reaction. So hydrazine or nucleophile. So addition of hydrazine nucleophile to the carbonyl carbon or carbonyl group. So we have CH3, then C. Remember that the oxygen atom has two lone pairs of electron, as explained before. Then on the hydrazine molecule, the nitrogen atom has a lone pair of electron on it. You see that this is electron rich, so it cannot go to this place. So you're going to find itself attacking the carbon, while the electron here is displaced at the same time. So you now have CH3, C, then the oxygen now becomes electron rich with 6 lone pairs, since we are displaced one of them, making the oxygen atom become negatively charged. And then have the hydrazine attaching itself here. The nitrogen atom becomes positive because it has shared its electron with carbon, making it electron efficient. And then we'll have CH3 here. So the next stage of the reaction will involve proton. Before we go to the next stage, is we have a proton transfer, just like what happened under ammonia addition. Proton transfer. The proton will be taken away from one of the, let me just expand this, one of these. So one of these, open it up. Proton means hydrogen will now move to the oxygen on top, while the electron here returns back to the nitrogen. So that will give us CH3, C. The oxygen now is bond, the hydrogen bonds with the oxygen. So the oxygen now have only 2 lone pairs remaining, and then CH3, and they will have NH2. Then the nitrogen now is rich with an electron. It's an electron rich. So that the intermediate formed, which is unstable. This substance is unstable. So we'll now go to the stage 2 or second step of the reaction. The second step of the reaction will now have addition of the nucleophile. Addition of the nucleophile. No, sorry, we're going to have loss of water, just like we observe in addition of ammonia. So you can see the difference. In addition of ammonia, water is lost after the hydroxy group have been protonated. You can rewind the video and see it. Water is lost after the hydroxy group have been protonated by hydrogen ion, but in this one, there's no protonation here. Water is lost without any protonation. So step 2, so no protonation occurs compared to addition of ammonia and primary amines, where protonation will take place before water is lost. But here, we don't talk about protonation here in this case. So you have this NH2. You can just put NH2 here, then N. So this is an electron pair. So water is lost. So from where do we get the water? The hydroxy group here pulls away the 2 electrons off, and then we'll remove a proton here, hydrogen ion here. The electron here returns back to the nitrogen, and at the same time, a double bond is formed. Double bond is formed, whereby this electron here moves to form a double bond. See what is happening? So, to form the water, the ion goes up to combine with the OH, form water. So, which pulls away 2 electrons, the electron returns back to nitrogen. While the electron on nitrogen comes back to here, to this point, form a double bond. We now have this CH3, then C, CH3, double bond, then N with a lone pair, and then NH2 there. So the compound is produced. This compound produced is called a hydrozone. So this is acetone hydrozone or a ketone hydrozone because it's formed from a ketone. So that's the compound produced. So if I use an aldehyde in the reaction, I'm going to get, the only difference is that this place will be hydrogen. It will be hydrogen if it's an aldehyde. I'm now going to what I call um, an aldehyde hydrazone, or if I use acetaldehyde, and I get acetaldehyde hydrazone. So this structure is something as writing CH3, since it occurs, there are similar groups, can bring them together. Then link to carbon, is the carbon there, double bond to nitrogen, and then to another ammonia. So this compound, the two compounds are the same compound we have on the board, so they're the same. So having done that, we are seeing how additional elimination reaction can occur with hydrazine. So let's take another example. Let's use the hydroxyl amine. So additional reaction with hydroxyl amine. The reactions of this this is also another kind of there's another kind of a hydrazine related compound. So reactions with this kind of compound undergo, the mechanisms are the same. If you understand one of them, you understand the other ones. So this time around, I'm not going to use a ketone. Rather, I will use an aldehyde. For example, let me use this one, CH3. Let me use an aldehyde. In this case, with this compound NH2OH, a hydroxyl amine. I remember, as I said, the oxygen is rich with 2 lone pairs. You have to show it. And then this nitrogen has a lone pair of electron on it. So you're going to move to attack the tetrahedral carbon as this electron here is displaced to make the carbon electron deficient. So we now have reversible process, CH3, then this, we now have oxygen now filled with 3 lone pairs. If the bond is delocalized, giving it a negative charge, then this, and then you now bring in the hydroxyl, the nucleophile, yeah, NH2OH. And because the nucleophile has shared its electron with the carbon, this naturally becomes positively charged. Positive charge. The next that will take place is proton transfer. Proton transfer will now occur. Proton transfer from the nucleophile here to the, from the nitrogen atom or nucleophile to the oxygen up. So let me open it up, or I can bring the structure down here also to make it easier for you to understand. So I have this. This is that. So now let me open the structure. There are 2 nitrogen atoms. I can put one up, bring one down. Is okay. This is also the positive charge still there on nitrogen. So, and then there's hydrogen here. So proton transfer means I'm going to pull one of the hydrogen atom and move it up, while the electron here returns back to the nitrogen. You see that? So the proton means hydrogen ion without electron. So we now have this intermediate produce, CH3, CH, and then OH. At this point now, the oxygen will use one of the lone pair to form a bond. There's a bond here, you should know that, with hydrogen. So the bond is formed here. So the oxygen is now left with 2 lone pairs. So I have 2 pair and a pair. There are 2 lone pairs here. Then, having done that, then we now have N, nitrogen, now having oxygen OH here, and then H here. Electron now return to nitrogen. Yeah, that's the center here. So we can put it anywhere here anyway. So this is the intermediate formed before we go to the second step of the reaction. So it's unstable. Being unstable, it will continue stage 2 of the reaction. The stage 2 of the reaction, let's see what's going to happen. The stage 2, which will involve loss of water. Remember that this reaction will not involve protonation or does not involve protonation, because compared to that of addition of ammonia, that's really different. The difference lies in the second stage. Look at the two of them. Addition of ammonia and addition of amines, primary amines, that will involve protonation in the first stage before the water is lost. But here, no protonation occurs here. So water is lost. So how is water lost? The hydroxyl group pulls away the two electrons and leave as OH. The hydrogen ion here moves to this to join the water. While the electron pair here, either this one or this one, will form a bond or double bond here. Will form a double bond here. So we now have CH3 at the final product, then C, then there's H here, and then we have a double bond, and then NOH, water eliminated. So that the product formed. This product formed is called an ozyme. So if since we started with an aldehyde, this is an aldehyde ozyme, and the aldehyde we use is acetaldehyde. So we can call that an acetaldehyde ozyme, OSIME, ozyme. So the structure can be, you can see write this compound as CH3. Let me put it down up here, CH3. Okay, if you can enter here, CH3, then C, then link to hydrogen. This is hydrogen here, then nitrogen, and then OH. So this compound and this are the same thing. So that is called an ozyme. You can see demonstrate the reaction using not only using an aldehyde. You can still use a ketone. If you use a ketone, you now form a ketone ozyme in the process. So having done that, we'll now go to the third reaction using a phenylhydrazine. Phenylhydrazine. Which is, the third is reaction with phenylhydrazine. So phenylhydrazine, the word phenyl indicates a benzene ring. So phenylhydrazine will be of this nature, NH2, because NHC6H5. So that the phenylhydrazine, that the compound NH2, so which is also can be drawn like this, NH2. So you don't get confused when you see structures. NH, phenyl ring is derived from benzene. So it's a compound, phenylhydrazine. So we're going to choose either an aldehyde or a ketone to demonstrate this reaction. The last one I did, I used an aldehyde. So in this one, I'll use a ketone, maybe acetone. So let's use a ketone CH3. Let's look at the first stage. Let's do it straight. First step is addition of the nucleophile, which is phenylhydrazine, to the carbonyl group. We're going to add this compound. So at the end of this process, you're going to see that the reactions involve similar stages. So let me use our dear acetone. A simple, so an acetone, remember that we have two lone pairs on what is in our carbonyl compounds, two lone pairs on oxygen. So plus you have this NH2, write the compound NH. Either you use the compound formula or the structure. There are two lone pairs of electron on the nitrogen. They are on the amino group. So the attack will move from this to the carbon, while the electron here, the pi bond, is delocalized to make the oxygen become negatively charged. So we now have this reversible process, CH3, then the oxygen atom becomes negative, having gathered 3 lone pairs of electron on it, making it negative 3 lone pairs of electron on the oxygen, making negative charge. Then we have CH3. They'll have the phenylhydrazine attaching itself here, NHC6H5. So this nitrogen is positive because has donated the electron to the carbon, or shared the electron to the carbon, making the electron deficient. The next step is, okay, we still continue. The next is proton transfer. Proton transfer from that molecule to this place. So let's draw the structure again and then open it up for clarity sake. So we have C, we have this. So proton transfer will now occur. You have CH3. So proton transfer, you have to open up the nitrogen. It has 2 atoms on it. Then NHC6H5. So proton transfer will occur here, whereby proton, as we said, means having an ion with an electron, will move to this point. And the electron formed here will now return back to the nitrogen atom. So that the proton transfer that will take place. Return back to the nitrogen atom. So we have that. So when the electron, that single bond means 2 electrons, as we know in chemistry. We return back to nitrogen. So now have this CH3, C, oxygen will now have only 2 lone pairs, since one of the lone pairs have been used to form a bond with hydrogen, which indicated over there. And then we have CH3, we have now N, H, and then we can put the hydrogen down, no problem. NHC6H5. So we have electron, a lone pair, because the electron has gone back. The single bond here is electron, which have been retrieved by the nitrogen atom. So go back to it. So this is unstable compound. This unstable compound will now be used in step 2 of the reaction. So you take note of that as we go to step 2 of the reaction. Then move to step 2 of the process. So in the step 2, what then will happen in step 2 of the reaction? So let's wipe the upper side of the board and continue with step 2. So remember, in step 2, we talk about what we call loss of water. There will be no protonation, as I told you. In this reaction, there is no protonation as compared to what happens in reaction of carbonic compound with ammonia and with primary amides, which protonation will occur before water is lost. But in this one, we don't have any water. That's the only difference between these steps and that of ammonia addition. So we have water, elimination of water. So how is water eliminated? This hydroxyl group will pull, I think there is an error somewhere. Going to this electron, this should have electron. Let's check it out and see where the error is and correct the mistake immediately. So okay, there's no error there. Is okay. So the hydroxyl group goes away, while the a proton here should be removed. Yes, which will join with the hydroxyl group. So the proton here is removed. At the same time, double bond is formed, where this electron returns here to form a double bond. So we now have CH3, CH3, and then this proton combines with any of the electrons to form water, of course, as we explained. Then this electron returns here to form a double bond with nitrogen. This electron that we have here, and two electrons we are left behind. This single bond means two electrons, which is given back to the nitrogen to make it certified to attestate, and then we'll have NHC6H5 as our final product. So this compound can be written in different form. You can see rearrange the structure. CH3 occur 2 times. So you can have CH3 bracket 2, then C carbon connected straight to the nitrogen, and then C6H5. You see the compound produced. So that compound is called a phenylhydrazone. So phenylhydrazone, because it formed from a ketone, so acetone phenylhydrazone. If it were to be formed from an aldehyde or acetaldehyde, it becomes acetaldehyde phenylhydrazone or aldehyde phenylhydrazone, depending on the aldehyde you use in the reaction. So you can see that. So that the product produced in that reaction. So that is the product. So we can be written in this form. We can as well put the phenyl group on top of the nitrogen if you wish, because it's bonded to nitrogen direct. So if you wish to put it that way, C6H5. It's the same structure. Or you can say write in this form, CH3 bracket 2C double bond N NH. Then so you can draw the benzene ring. Since phenyl means a benzene ring that has lost one hydrogen atom. So they all boil down. These structures are all the same thing. So having done that, we're now going to the third the fourth reaction, which is reaction with 2,4-dinitrophenylhydrazine. So reaction with 2,4-dinitrophenylhydrazine. So that is the third reaction we want to look at. Now, we use a ketone in the former one. Now, this one, we're going to use an aldehyde. We're going to use an aldehyde to do that. So, I use the simplest aldehyde. We're going to use acetaldehyde, or which you can call propanone, 3-carbon propanone. So, with this compound, which is a complex compound for the matter, 2,4-dinitrophenylhydrazine. So that is structure. Okay. So this is number 1 position. Number 2, nitro is NO2. Number 3, and then number 4. So that is the substance reacting with this. So give us some products or a product. Now, in this reaction, we look at the first stage. Just like we saw in the previous examples, the first stage is addition or attack of the nucleophile. Addition of 2,4-dinitrophenylhydrazine to the carbonyl group. So that is it. So we have the reaction, the first stage. Remember, as we say, the oxygen atom is blessed with 2 lone pairs of electrons, while the nitrogen atom in the amino group or the phenyl compound of the hydrazine compound has a lone pair on it. So you have this. So you don't have to be afraid of structure. You follow the same process as we discussed in other ones. The same process. So this is electron rich, so you're going to attack the central carbon while this electron here displays. See the same process we are applying. So you now have this CH3. Then the oxygen atom now will be having SS 6 6 electron. There is 3 lone pairs. That's what I mean by 6. 2, 4, and then that make it will become negatively charged. So negative charge. So CH3, and then here we bring this group down. Bring it down to form a bond. So you see that. So you have to draw the structure the way I've seen it without any mistake. NO2, number 2 position, number 1, 2, this is number 4. That's why it's called 2,4-dinitro. The group is called nitro. So having obtained that, what the next thing you should do? The next thing you should do is that we're going to have a proton transfer. But before we talk about the proton transfer taking place, the nitrogen are giving this amino group this electron to share with carbon. That makes the nitrogen become positively charged. Make electron deficient, the nitrogen here. Then the next step of this reaction will not be nothing but going to have what we call proton transfer. Proton transfer. The proton will be transferred from this amino group. So instead of drawing the complex structure, what I'll do is I'll open it up. How do you use 2 here? I'll put 1 up, 1 like this, and 1 down. So proton means hydrogen ion will be transferred to the oxygen on top. The electron that it leaves behind, the 2 electrons that the bond, return to nitrogen. So we now have this intermediate CH3, COH, leaving behind. Now you now have 2 lone pairs, CH3, and then I have NH, then NH here, then the phenyl ring, then nitro group on number 2, and then number 4. And then of course, the nitrogen atom will now have a lone pair. Because this bond is going to be taking the 3 by nitrogen to give you a lone pair here. So having obtained that this molecule is unstable, being unstable, we're now going to go to the second stage of the reaction. Remember that the oxygen has 3 lone pair before, so use 1 to form a bond with the proton. The proton means hydrogen ion without any electron. That way you have 2 lone pairs remaining on the oxygen. So having done that, we'll now move to the second stage of the reaction, or step 2, which is loss of water. So to give us the final product. So step 2, we'll have this, we'll draw the unstable molecule up, then CH3, then nitrogen, H, NH, okay, NO2, NO2. So we'll have that. So water is lost. The hydroxy group is eliminated. It goes with the 2 electrons. Then the hydrogen atom remaining here, the proton will now join the hydroxy to form water molecule. Now this electron here, this lone pair, will now change position to form a double bond there. So you have the final product, which is going to be CH3, CH3, double bond, N here, and then complete the structure. So we have to show electron movement. This is the phenyl ring, number 2 nitro, 1, 2, 3, 4 under nitro here. You see? And remember that one electron here formed the double bond. The proton left without an electron. So electron here, this single bond means to electron return back to the nitrogen to complete its state. Or its pentavalent state. You can see 2 electrons you use here. For the one 2 electrons I've used also 4, making it 1 electron here, making it 5. So that gives the final product. And that product formed in that reaction is called a hydrazone. So it's 2,4-dinitrophenylhydrazone. 2,4-dinitrophenylhydrazone. ZONE. Since the starting material is a ketone, so this is a ketone, or this acetone. Acetone should be in front. 2,4-dinitrophenylhydrazone. If I use an aldehyde, it's going to be an aldehyde 2,4, maybe an acetaldehyde. Acetaldehyde 2,4-dinitrophenylhydrazone. So, having done that, we're now going over to the 5th reaction, as we are coming almost to the end of the lecture. Reaction with semicarbazine. You see, they all undergo the same process. So if you understand one of them, if you understand the reaction with hydrazine, or you can still understand that the same process is involved in reaction with hydrazine-related compounds, which we are using semihydrazine, semicarbazine, hydroxyamine, and so on. So the 5th is reaction with semicarbazine. So I can use an aldehyde in this case, since I used ketone in the previous case. So I use an aldehyde, like acetaldehyde in this case. So H, double bond here, oxygen, or anywhere you want to put it is okay. With semicarbazine, which has this structure, H2N. This is a amino group of the. This is a part of the. Remember, this is part of the hydrazine. Then the Z group, which should have been here, you then replace another group, NHCONH2. So this compound is called a semihydrazine. Semicarbazine. Sorry, semicarbazine. Carbazide. Semicarbazide. So that's it. So in this reaction, the same step is observed. Remember that this nitrogen has a lone pair, and this oxygen has 2 lone pairs here. So the first stage will be attacked by the nucleophile, or by the semicarbazide. So that's the first step, whereby the electron pair goes to attack the carbon, which should be electron deficient. And to make it electron deficient, the electron here will shift or move out, or go to the oxygen atom, which is more electronegative. We now have CH3, C, then the oxygen will now be having 6 lone electrons, or 3 lone pairs, 6 lone electron, 2 forces, or pairs, 3 lone pairs. Then have hydrogen here. We now attach this group, NH2, the semicarbazide, CONH2, giving this one a net positive because this electron was used to form a bond with carbon. So having done that, the next is we are going to have what we call proton transfer. The proton transfer, whereby the amino group will lose a proton, which will go straight to this oxygen atom up to form a hydroxide group over there. And then electron here return to the nitrogen atom to make it electron rich now. So we now have CH3, C, then OH. Also now left with 2 lone pairs, because one of the lone pairs have been used to form a bond with hydrogen, as you can see. So you now have H, and then nitrogen, then NH. Then this will have NHCONH2. So having done that, so the electron here, this single bond now returns to nature, becomes an electron pair, making it rich. So this molecule is unstable and will be used in the second stage of the reaction, just as we have described in the other procedures. So having done that, the second stage of the reaction, what then happens? We move to this, the second step of the reaction, or step 2. In step 2 of the reaction, CH3, CH, then oxygen with double bond, with 2 lone pairs, sorry, and then that second stage normally involve elimination of water and formation of a double bond. That what might takes place here. If you look at the other ones we have done, the examples we have taken so far, so water is removed. So water is removed. So and high water, this cannot form water alone. The hydrogen ion, the proton, move up to join the water, giving you H2O. While the electron here, we change the lone pair here, will now change its position to form a double bond there. So you now have CH3, CH, double bond produce, then N. Okay, what have been removed? So plus what have been removed or lost. Or you can say minus water here if you wish, without putting the plus water this side. So, and then look at the, we didn't get it right. I think, well, I was supposed to complete the compound. There's NHCONH2. That is part of the molecule, should be complete. So, the here should be NHCONH2 at the final product. But before we conclude, we'll see that this electron have moved to this point. This proton will be removed. There's a bond here. The bond will return back to nitrogen to form another lone pair, to make it certified to its outer state. We'll come back to nitrogen. So you have to be careful of electron movement when it comes to organic chemistry. You don't just write anything that you don't like, that of your own interest. You don't write nonsense. So that is the compound formed. And that compound is called a semicarbazone. So this is a semicarbazone. So from semicarbazide, we form semicarbazone. You can see that. So we'll now move to the ending part of the topic. We're going to go to what's called the Wittig reaction. Wittig reaction, another example of addition elimination reaction in carbonyl compounds. So we'll now look at Wittig reaction. It's called by Wittig. So the reaction is all about the reaction of carbonyl compounds. So it could be a ketone or an aldehyde with a phosphorus halide. With a phosphorus halide to produce an alkene. An halide is a molecule with adjacent opposite charges. So that's the nature of an halide. So it has opposite charges bearing positive and negative charges. The one bearing negative is carbon, and the one bearing positive is phosphorus. That phosphorus is bonded to a triphenyl group. Triphenyl group bonded to the phosphorus. So that is an halide. So whenever an halide reacts with either an alkene react with either an aldehyde or a ketone, it leads to formation of an alkene. So we're going to take an example of this reaction. We'll take a ketone, for instance, and then see how it goes. You can use acetone. So for the reaction, you can use acetone, CH3. I have this acetone, CO, reacting with a phosphorus halide, and then we have that. So the general structure of a phosphorus halide is this RC, then phosphorus, the phenyl group, of the triphenyl, here is negative, here is positive. And you know that this stands for alkyl group. So I can use any alkyl group. I can use similar alkyl group, like I can use a CH3 methyl group here. And then that is it. So that is an iodide. So you see that. So let's see how this reaction goes. So the reaction occurs also in two steps. So the first step is the negative carbon of the iodide attack the carbonyl carbon to form a beta. So negative carbon of the iodide combines with the carbonyl carbon to produce an intermediate called a beta, B-E-T-A-I-N-E, a beta. The negative carbon of the carbonyl compound of the iodide, attack the carbonyl carbon form a beta. So let's see how the reaction goes. That's the first step of the reaction. Let's see how it goes. So the negative carbon, let's bring it down a little for clarity. This is our acetone or ketone. So the negative carbon is assumed to have excess electron. That's why I have negative charge there. Why this is positive? We attack the carbonyl carbon. We're supposed to be electron efficient. But remember that this oxygen has 6 electrons on it already. So for you to attack, this carbon should be made because the electron here will now first of all shift, delocalize to make this carbon electropositive somehow. So when I have CH3 carbon, oxygen will having 6 electrons, negatively charged. Then we have this one combining here with bring its electron to form a bond with the carbon, which is partially or electropositive. And then we have this intermediate formed. So you can see that. So we have that. So all we have to do is we rearrange this structure in a way that, remember that this phosphorus is positive charge. We arrange this structure in a way that the oxygen atom will be adjacent to the positive phosphorus. So what do I mean? In same thing, we have push the methyl group to the other side. The two methyl group to the other side of the carbon, and then move the oxygen to this side. You can see just the same thing but rearrange in configuration so that the carbon atom, the oxygen atom which is negatively charged, will now have attraction for the positively charged phosphorus. So have that intermediate produced. Then the next stage is now the beta. This is called a beta. What do I mean by a beta? A beta is a molecule that have non-adjacent opposite charges. Look at the difference between an iodide and a beta. In the iodide, the atoms are adjacent with opposite charges, close to each other, negative and positive. So, but in the beta, these two atoms are negative, but they are not adjacent because this one is connected to this one. What is connected to a neutral atom? This one is connected to another neutral atom. But in this case, the charged particles are connected, atoms are connected together. So this is an iodide, a molecule that has two adjacent opposite charges. A beta, a molecule that have two non-adjacent opposite charges. So you see the difference between the two of them. So we'll go to the second step of the reaction. Step 2, the beta undergoes elimination of triphenyl phosphate oxide. So step 2 is elimination of triphenyl phosphate or phosphorus oxide from the butane. That is one stage of the reaction. So we now have this CH3, CH3, so that the butane produce down there, C6H5, 3, there's phosphorus here, and then there's oxygen there. So you have this. Before the rearrangement commences, a bond will be formed between oxygen atom and the phosphorus. Remember, the oxygen atom has 6 electrons, so one of the lone pairs will be used to form a bond with phosphorus. So we now have CH3, CH3, then C, then oxygen, forming a bond here with the triphosphorus substituent. So you have that produced. So that is it. Having done that, so when the bond is formed, this electron now remains 2, and the charges will now disappear. So one of the lone pair have been used to form this bond. So we don't have 3 lone pairs now, we now have only 2 lone pairs and oxygen. So having done that, we're going to have a kind of rearrangement that will now eliminate the phosphorus oxide. So electron here with this lone pair, this single bond will shift to this bond, while this one will shift to this side. So that what would happen. So at the end of the day, we're going to have